welcome you all for the Atal Online FDB. Now we move on to session 5, which focuses on flight test instrumentations. Let's take a moment to honor and introduce today's resource person, Sri David Livingston, Group Director, Aeronautical Development Agency, Bangalore, who bring a wealth of expertise for today's session. He has 24 years of experience at National Flight Test Center, Aeronautical Development Agency, in the field of ground telemetry and on-board flight test instrumentation. He has contributed in the field of onboard instrumentations, weapon instrumentations, and special instrumentation scheme for flight testing. He is the recipient of AESI of Aeronautical Equipment Award in the year 2008. Presently, he is a group director at National Foreign Trade Council ADA. We welcome you, sir. We are very eager to hear your insight. Sir, please take over the session.
Am I audible?
Yes, sir.
Very good evening to all of you.
Good evening, sir.
So thank you very much for the kind introduction. So I'm very much interested in talking to the group of teachers because I was teacher at the beginning of my career. I worked in Institute of Road and Transport Technology, Karunia Institute for some time. Then I worked in Sivagasi Maposhalam Engineering College before I got my placement in Aeronautical Development Agency, Ministry of Defense, Government of India. So I'll be presenting about the flight test instrumentation. Right. So shall I share my screen? Okay. PPT. Okay, 1 second. Are you able to see the screen?
Yes, sir.
Yes, sir.
Are you able to see my screen?
Yes,
Yes.
sir.
Oh,
We
wait.
can see the slides.
So in this presentation, I'll be touching upon what is flight test and its process, and the ground test, and we'll come upon to this thing, flight test instrumentation. That has got two parts, actually onboard flight test instrumentation, where we instrument an aircraft or missile or helicopters or whatever it is, right? That is, we call it as onboard instrumentation. Then to receive the signal and get back to the original signal, we need a ground station. Okay, that is ground telemetry. I'll be taking some practical points about the telemetry and some cases of weapon instrumentation. And if we get time, we'll go to the last session. Before getting into that, starting the presentation, I would like to introduce our organization. You would have seen most of you will be knowing about the Tejas, which is inducted into the Air Force. So we are involved in the flight testing. It has completed more than 5,000 test flights without any incident. It's one of the greatest achievements. So I'll just show, for those who are not aware of this program, I'll show a 2 minutes video. Are you able to see this video?
Yes, sir.
Yes, sir.
Are you able to see the video?
Yes, sir.
Yes, sir.
Okay.
So we cannot see the video, only we can see the screen. Sir,
Yes.
we can see only the screen, not the video.
Oh, video is not there?
Yeah.
Okay. Or Okay, okay. So you're not able to see the video, right?
Yes, sir.
Okay, fine. Okay. So I'll stop sharing because some issue is there. 1 second. Are you getting it now? Are you getting it now?
Yes, sir. Yes, sir. Now we can see the video.
Thank you. Let's go back to the presentation. Are you able to see the video now? Sorry, my screen. Are you able to see my screen now?
Yes, sir.
Okay. See, flight test process is actually when you want to make an aircraft, for example, you have to have the requirement first from the Air Force. That we call it as air staff requirements, right? Then the design of an aircraft will start, right? So when the project definition is made, then project definition review comes, then
Sir,
comes the
we can't
detailed
see the
design of the
screen,
project.
sir. Sorry,
Then,
sir. We can't see the screen. Only the video we are able to see here.
okay, so there's a delay, is it? Okay. 1 second, I'll come back. I'll close and open the screen. One
Yeah,
second.
you have to switch back to the other screen.
Okay. I'll once again share my screen. Okay. I think you are able to see the screen now, right? Are you able to see my screen now?
Yes, sir. Yes, you can go ahead, sir. Yes.
Yeah. See, now this is actually after this preliminary design review, detailed design, then critical design review will be there. This is the process, right? Then the lot of rig testing will be there. The concept, evaluating the concept. A lot of simulation studies and other things will happen. Then slowly the parts will be fabricated and it will be going through a lot of rig testing. Then it will be assembled. It's a huge process which involve hundreds of work centers across the nation and abroad, right? So then this aircraft will go for the aircraft level testing, the ground testing. Then it will start flying, right? So we'll be covering, starting this thing, discussing about the flight test part. See, flight test is the process of collecting quantitative and qualitative data of flying machine with a view to prove and improve the design and evaluate the performance. See, this is the objective of a flight test, any flight test, aircraft or missile program. See, when you come for a flight test, this is the overall domain of the flight test. I have taken a sample performance thing. It is a plot versus pressure altitude versus Mach number. See, this pressure altitude is the how much the altitude the aircraft can fly, right? So our aircraft can fly up to 15 kilometers height. Okay. And this is the Mach number. Okay, Mach number is the ratio between the aircraft speed to the speed of sound. It's Mach number. The aircraft can go. If the aircraft speed, all the commercial aircraft will go very small, this low speed below 1 Mach number. The transonic is from your subsonic to supersonic. It is 1 Mach number. And most of the fighters goes to 1.8, almost to up to 2, more than 2 also. These are the fighter aircraft. Right now, some hypersonic flight missiles and aircraft have come. They can go 5 times the speed of sound. That is Mach 5.0 or more. Right. Now the flight test, when we do that, in the process of certification, we need the instrumentation plan. An aircraft needs to go through the certification process. For that, we need to instrument the aircraft. So we should have an instrumentation plan. What and all we are going to test? The aircraft has got plenty of system. It has got avionic system. It has got a flight control system where the actuators, pilot input gives the input, the actuators respond. Right? Aircraft has got a brake management system, and the aircraft has got fuel system, propulsion, that is the engine of the aircraft. Then it is controlled by control law of the aircraft. So many things are there. Plenty of systems. Okay, then cooling system. All these things has to be planned. So every subsystem of the aircraft and the overall performance of the aircraft needs to be tested during the flight test. Right. So for that, we need to have, the aircraft has got sensors. In addition to that, we should have a thorough instrumentation plan for the aircraft. See, why we test is basically to evaluate the performance. And see, in the test, a lot of risks are there. Suppose you want to test an engine, right? So new engine made in India, it's a Kaveri engine, for example. If you take, then it is always a risk, right? It's not a proven engine, only it is tested in the test bed. If you want to put it in the aircraft, so a lot of risk is involved, right? So it's a manned mission, right? Human being is flying, so it's a single engine aircraft. If you want to put in an engine which is not proven in flight, the risk is involved. So that is this is a statement of Warren Hall. Flight testing will never be risk-free, but the risk must be managed to an acceptable level and balanced against the technological gains. See, once we start flying, take the risk and fly the aircraft. So we can prove the engine. We can prove the new radar systems, right? All these things, you need to take a risk. Some systems which can be tested only in flight. So many systems, right? After ground test, anyhow, when you put together, it has to work as an integrated system during flight. So many things, a lot of risk is involved. So we have to manage the risk. See, design and development, so many organizations are doing. Our Tejas SADA is doing this Mach 1 program, Mach 2 and AMCA program, and IJT program, that is Intermediate Jet Trainer by HAL, and other ALH, LCH, LUH of HAL, right? All these helicopter programs, and the small transport aircraft program by NAL. And these are all the UAVs by AD, Lakshya, Nishandan. See, now the flight test is for proving the design verification, mainly functionality of the aircraft as a whole, and whether it is complying to the specification and whether it is covering the envelope, and also the environmental coverage. The aircraft has to fly in very cold condition with very hot places. So whether it is doing all these things, and as a whole, the aircraft, whether it is reliable or not. Right. These are all the design verification for the flight testing. Right. So there are different types of flight testing. That's the research flight test, prototype flight test, and production flight test. These are all the different stages of flight testing. And our aircraft, we started with technology demonstrator 1, TD1 and TD2. Then we started with PV1. Prototype vehicle 1 and 1 to 3, then limited series production we started, then it has LSP 1 to 8 like that, then SP series, which already has it is inducted in the aircraft, Air Force, right? Now, as I said, the aircraft model needs to be tested in different scenarios. This is a case of wind tunnel testing, right? See, you see the aircraft scale model will be put into the wind tunnel and various, you can blow the air of that much of aerodynamic effects will be simulated in the ground, on the ground. In this, the different sensors, like a surface flow, how it is. All this model also will be heavily instrumented outside for your structural clearance and mainly for your aerodynamic behaviors, how a weapon is following and how it is the airflow is happening, what is the effect of that on the wing. So scale model will be tested. Some amount of testing we can succeed in the wind tunnel. Then after the assembly of the aircraft, again the ground test will start. Actually, there are different types of ground tests: ground structural test and vibration test. They are here. Thousands of strain gauges and accelerometers will be put onto this aircraft, and you can see the load is applied to the aircraft. Okay, hydraulic load will be applied on the wing at various places, and the system will be cleared for flight. Right. Now, if you go through, in addition to that, subsystems like a fuel system, actuator system, and the engine propulsion system and environmental control system, all systems, subsystems will be tested. Here also instrumentation is required. They are all called ground instrumentation. Right. So this ground instrumentation will be evaluated, and based on that output, then we will get a confidence. Okay, the system is performing. Then it will be pushed to the aircraft. See, now coming to the flight test instrumentation. Flight test instrumentation, if you take an aircraft, okay. So you are given with a task of acquiring some 800 parameters, right? 800 sensors and some bus parameters, mil bus parameters, or so many other parameters needs to be acquired. This is a typical block diagram, and this is a simple block diagram. If you see, this instrumentation system has got sensors first, right? So it's a pressure sensors, temperature sensors, accelerometer for vibration, then the displacement sensors. All then you come the digital buses, mil bus, RS422. Like that, the different types of sensors are available, which we need to acquire in the aircraft. Strains and the video, high-speed video, and all these things needs to be acquired, right? So this is basically a network-based architecture, and it has got a powering system. And coming to this side, if you see, you can have a RF system, right? So it has got transmitters, then power amplifier, power dividers, and all. Then the antenna. See aircraft, if you see aircraft on the top of the aircraft fin side, you put some antenna. But when after the aircraft takes off, you won't be able to see that fin. It will be always on the top most of the time. So bottom antenna should be there to get the signal when the after aircraft takes off, right? So this is a typical flight test instrumentation system. We'll try to see some of the components of the system and see how they are implemented. What are the points to be taken into account in each system, right? Now, when you take the onboard architecture, this is a simplified one. See, basically, measurement sources are broadly as analog transducers and avionics buses. And the data collection by so many data acquisition systems in the aircraft, and the data is getting recorded on some recorders. Right? Previously, big recorders were used. Now, solid state, very miniaturized recorders are used. Then comes the transmitters, and if you want a secure communication, you can include encryptors also. See now the type of analog sensors, right? So if you take, if to measure the acceleration, vibration, and shock, we use basically accelerometers, right? There are different types of accelerometer, piezoelectric, piezocapacitive, and all these accelerometers are there. And these are all of instrumented at various places. I can show some of the installations, right? Then comes the pressure transducer. There are different types of pressure transducers. That is to measure the line pressure. Suppose you want to measure the line pressure of gas line or a hydraulic line, a fuel line. See, this kind of sensors are used. This flat type of sensors are for surface pressure sensors. In addition to that, there are differential pressure sensors. Say, for example, you want to measure the differential pressure, you use the differential pressure transducers. Then comes the LVDT. LVDT is mainly for linear displacements. Then we can see, so in the undercarriage system or in the naval version, the hook, how it is getting engaged, how much it is stressed. Okay, all those things. Then the aircraft, after it lands, the nose of the aircraft, no, it moves, it wobbles little. And how to catch that wobble? It is basically a rotary. RVDTs are used, right? That is rotary variable differential transducer, right? Then the strain gauges. There are different types of strain gauges. I put some foil type here, right? There are different types of foil type strain gauges. In this also, there are rosette there and the linear gauges are there. These gauges will be stuck onto the aircraft. Mainly, say for example, new aircraft comes, they give a requirement of around 300 to 400 strain gauges, which will be stuck at various airframe structures and in various landing portions. Wherever they suspect a lot of load will come, there and also it will be instrumented with strain gauges, right? There are different types of instrumenting that. It is a quarter bridge strain gauge, then full bridge strain gauge. So many varieties are there. It's for mainly to measure the your linear or shear or torsional loads on strains, right? Coming to temperature, it is basically thermocouples and RTDs are used. These RTDs are basically for low temperatures around 250 or 300 degrees Celsius if you want to measure, right? So it is for RTDs are used. Thermocouples are used for relatively high temperatures, right? Here I put some flow. In addition to that we have seen for temperature, flow sensors are very critical in the thing. Suppose you want to find out the thrust of an engine when it is flying, right? So we need to get all the flows to compute the thrust, how much the engine is producing the thrust. That is you have to have so many parameters. In addition to that, flow is a critical parameter. Okay, main flow, how the fuel is flowing to the engine, right? So to get that kind of thing, you need flow meters, right? Then I have shown here the RVDT, that is for rotary displacement moment. Here on different, this thing LVDT is shown, right? These are for linear displacement, this for flow. So here that's this is uniaxial strain gauge. It's a single channel is there. There are some strain gauges where we need to acquire 3 channels together. You can see here there are 3 strain gauges in a single foil. These are called rosettes. See how the designer wants to evaluate the loads coming on various systems. They stick the strain gauges. From there, it will go to our data acquisition system. Right. Okay. When you come to a transducer, see, basically, we have to plan the instrumentation in such a way that so a person wants to measure the engine vibration or structural vibration. So the frequency response of the sensor, which is to be put there, varies, right? Some will be only a engine, right? So it will be a rotary vibration. It will be a fixed frequency component will be coming. So they will give the sensor response. I need only 500 hertz response. Some people will, structural people will say, this place I want sensor accelerometers of around 2K response. So if they say 2K response, we have to sample more than 4K to get the actual components. Then the level, see any transducer you have output level is defined, right? Some may be very, some strain gauges and some pressure lines and some strain gauges mainly it will be so small signal. It is the millivolt signal, right? The output levels will be very less. Some 200 millivolts, some strain gauges even 30-40 millivolts, right? These are the things. Then the power requirement comes, right? Whether we have to excite the sensors. So all pressure sensors, if you take, we need to excite the pressure sensor. There will be lines for exciting the sensor, then there will be lines for getting the output. So data acquisition system, the modules will give the excitation as well as it will take the output from the sensor. Say for example, if you take a power pressure sensor, it will have 4 lines plus a shield, right? So 2 lines will be some 10-volt excitation will come, and for in the other 2 lines, output will go to our data acquisition system, right? And the size, you cannot put very big sensors in the aircraft. The aircraft, fighter aircraft, is the space available in the aircraft is very small, right? We need to have, we need to go for very miniaturized, and the thread type, everything should suit the line. So we have to select the sensor and the thread type with the adaptability, mechanical adaptability to the lines and various parts in the aircraft, right? So every single parameter has to be selected and consolidated to procure the sensors, right? Then the environmental specification. You cannot buy a small industrial sensor and put it onto the aircraft. We should go through that the environmental requirement. Suppose if you want to put a sensor in the engine bay or somewhere where it is very hot, we need to have a sensor which withstands that kind of temperature. Suppose you are putting some temperature in the cockpit, so we can have some leeway. So we can have a sensor where which can work from even from 10 to 30, 40 degree Celsius sensor also can work in the cockpit where the temperature is maintained for the pilot, right? So these are all the things to be taken care when selecting a sensor for the aircraft. See, in the aircraft, there are 2 types of sensors. Right? They are called system in the aircraft, developmental flight testing. They are called system sensors and FTA sensors, right? System sensors, I have seen this. So for this page is, I've shown some of the system sensors, right? System sensors are the sensors which are a permanent fit in the aircraft. See, I told you the aircraft will be flight tested and it will be proven and it will be going to the Air Force for fighting. That time there will not be any instrumentation there, right? But whereas the system sensors in the aircraft will remain in the aircraft throughout its life cycle, right? Maybe aircraft will be there for 30, 40 years, right? So throughout the life cycle of the aircraft, when it goes for war or whatever it is, this sensors will be always there. Whereas instrumentation sensors will be removed, right? Once the flight testing and operational clearance is achieved by the aircraft, then this instrumentation FTA will not be there. So that's what I wanted to tell about the system sensors and FTA sensors. System sensors remains in the aircraft, whereas FTA sensors are only for flight testing. See, I will give some of the installations of the sensor. Say, for example, here I put one line pressure sensor. So you can see this particular line where the sensor is put. Okay, you can see this line in the aircraft. It is a hydraulic line, and you can see the sensors mounted on the line. See this, you can see here in the landing gear. The landing gear in this, our aircraft has got one nose landing gear and 2 main landing gears. Okay, the aircraft lands with main landing, then we lower the nose and touch. So heavy load will be coming onto this landing gear. So a lot of strain gauges are put onto the landing gears. Okay. This is bay temperature. This bay temperatures are normally RTDs are used, right? See, RTDs are used in this bay temperature. This RTDs, how they are excited. Here you see RTDs, you will bear me 3 lines, right? One output, okay, you can see the output, and there will be an excitation. RTD will also just a resistance, right? This RTD sensor is just a resistor. We have to give a constant current to the RTD, and the voltage drop will be taken and it will be covered by the data acquisition system. The data acquisition system job is to get the output from the RTD, but the job of the data acquisition system is also to supply the current, fixed current. See, this resistance is variable based on the temperature, but the current is constant. So whatever the output variation will be related to your temperature. Now I'll show some of the installation of the external missiles and the drop tanks. This kind of accelerometers will come. When these are all attached to the external to the aircraft. A lot of vibration will come when the aircraft is going at a speed of, say, for example, 1,200 kilometers per hour or so. So the heavy vibration will come in the aircraft. So to capture those things, these are all the accelerometers mounted on the aircraft external components. See, now this is a flow sensor, how it is installed. You see, this is the flow sensor installed in the engine, one of the parts of the engine, right? So here you see the line is remote, this is the input line and this is the output line. Flow sensor is introduced in between to find out the flow. Flow means flow rate. It's a fuel flow rate. Basically, it will be in liters per minute or gallons per minute or so. The flow sensors, right? How much fuel is going to the engine? It's a flow sensors. There are some potentiometers are used in this kind of actuator extension and all those places. And current transformers are measuring the current through the, see, in the aircraft. So 1 minute, I'll take a break, urgent call. Hello. Ranjit, I'm in a presentation. Actually, can I call you? I'm doing a presentation. I will call you. I'll call you after this. Okay. Okay. This is basically another accelerometer fitment. Then in addition to this, these are the parameter sensors we need to acquire. In addition to that, avionics buses, where thousands and thousands of parameters will come from different line replaceable units in the aircraft. Say, for example, say engine control system is there, right? And your environmental control. These are big computers and the navigation system, right? These are all big computers. They all communicate with each other in the aircraft, right? Through the MIL-bus 1553 standard. This avionics buses, they are so many RTs, remote terminals will be connected. They are all different computers which communicate with each other for the aircraft to function properly, right? These are all the avionics buses. The main communications through MIL-bus 1553. This is a digital avionics bus. In addition to that, other standards are also there. RS-232, RS-422. RS-422 is mainly used for flight control system in our aircraft. It's a quadruplex system. It's a 4-channel. The multiple redundancy is there. So when the pilot gives the input, the actuators should move to turn the aircraft to different directions, right? So these are all the signals which are coming from the all the pilot inputs and the response of the aircraft. All we get in this flight control computer. That is the signals coming from the flight control computers are in the form of this RS-422 type of signals. You know how much this RS-422 signals vary and how much it drives and all those things. Then some of the things, some of the videos come through Ethernet. See, suppose some of the units, say, pressure scanners are there. This pressure scanner gives the output through, in the Ethernet form. That also needs to be acquired by the data acquisition system. So these are all the different types of signals. In addition to the basic sensors, digital signals from various LRUs, that line replaceable units of the aircraft, needs to be acquired by the flight test instrumentation's data acquisition system. See, in this entire scenario, this FTA system will be just a monitor. The aircraft will have huge amount of communication. Everything will be monitored by and recorded by our FTA, flight test instrumentation system, and the critical parameters will be transmitted to the ground station, right? See, all the entire information in the aircraft cannot be transmitted to the ground station. Selected critical parameters will be transmitted in real time so that the ground station receives those things and we can take the signals out and we can monitor those signals on ground station, right? In addition to this kind of digital signals, we need to have a video, right? There are different types of video signals from the aircraft. See, if a pilot has got a head-up display, and there are some other types of cameras which are mounted to see the external events. Suppose you want to refuel the aircraft yard to yard. So mother aircraft will be having the fuel tank. This aircraft which is going, the fighter will have to go and get the water. It has to be refueled from the tanker aircraft. Okay. So this event has to be monitored by a camera, say for example. So this cameras are mounted there. These are all qualitative videos. See, there are some quantitative videos are there. Suppose a bomb is released from the aircraft. There are some cameras which has got frame rate of around 200 frames per second to 1000 frames per second, right? So these cameras are fitted on the aircraft for measuring critical events. Say, for example, you want to measure the bomb release from the aircraft. So cameras are fitted to focus on these bombs and missiles, and a lot of stickers will be put. You have to calibrate. If you want to have a measurement, you want to have a quantitative data, right? Say, for example, if the bomb is attached to the aircraft, when the trigger command is given, this piston will push the bomb down from the aircraft. So the bomb will have different movements when it is released from the aircraft. It has got a pitch, roll, yaw, and other movements like the X, Y, Z direction. The bomb will move and goes towards it will be falling to the top, right? So how well the bomb is getting released from the aircraft has to be certified, right? Suppose in the release portion, when the bomb is hitting the aircraft, then what will happen? It will damage the aircraft, right? So these are all the quantitative video. To get a quantitative video, we need to put up plenty of stickers, and these markers has to be laser calibrated, and the fixed part and the movable this bomb also will have these stickers, right? This the video can be processed further to these frames can be processed further to get the actual your X, Y, Z displacement and your all the attitudes, pitch, roll, and yaw attitudes. Now we have seen some of the sources of the signals. We have seen a lot of types of sensors used, and we have seen the digital buses used in the aircraft, and we have seen what do you call the video sources, right? So now let us go to the data acquisition system. This data acquisition system is a center of the instrumentation system. It conditions, digitizes, and formats the input data signal for recording and transmission, right? So two purposes: the data acquisition system acquires the data and dumps it into the solid state recorder onto the aircraft. Okay, so huge amount of data will get recorded in the solid state recorder. Every information will get recorded in the solid state recorder. Whereas a selected amount of stream, so two streams will get generated. Two PCM, pulse code modulation signals will be generated. One is very high data rate in the order of, say, for example, 30-40 Mbps data rate that will go and get recorded, and low data rate signals in the order of, say, for example, 2 Mbps or 3 Mbps will come for the transmitting. Okay, and a ground station, there will be data processing system to segregate the signal. Okay. These are all the typical data acquisition system. You can see the data acquisition system has got various parts. Say, for example, these are the modules. Each connector is a module. We can remove the module, right? See, some modules, you can see the module. These are all some of the imported and Indian systems are there, right? So these are all the data acquisition systems which can acquire various types of signals. I'll show the typical data acquisition system. It has got these are the modules. You can see the modules. The initial module is basically the PCM encoder module. See, whatever this unit acquires, it has to be encoded in the pulse code modulation PCM format. Okay. Then it has got this onboard processing module. Suppose you want to do the computation onboard itself. We want to compute the components onboard itself and send to the ground station. This onboard processing module is also there. And this analog data acquisition module, you want to acquire some voltages, millivolts or some voltages. Some cards analog data acquisition modules comes with what? You can have excitation also, and some can be directly record the voltage without excitation based on the requirement in the aircraft. Okay, this is RTD data acquisition modules for acquiring the temperature. This RTD is a residue temperature detector, RTD. This is basically this separate module which excites the RTD and gets the output. Okay, Say, for example, each module will have maybe 16 to 24 channels based on the type of the module. That many number of channels will be recorded in each module. Huge amount of wiring will be there, right? Then the thermocouple data acquisition module, right? Milbus, I told you, Milbus 1553 is basically the complete bus data which is flowing in the aircraft can be monitored and recorded in our data acquisition system. Then this RS2 data, RS422 data acquisition modules are there. That is mainly for your flight control computers. Then Ethernet acquisition module, discrete acquisition module. That means some weapon discrete. Discrete acquisition module is basically for its optocoupler based module where the weapon discrete. Say, for example, you want to fire a missile or a gun in the aircraft, right? So it will have a lot of control signals will be going, right? So when you initiate the trigger, so all the digital pulses, all these things will be get excited. Suppose you want to have record this discrete events. Okay, this discrete acquisition modules are used. Then the memory module. Some modules we can record the data itself there. Right. But typically, we'll take a case of a thermocouple, right? This is a K-type thermocouple. Mainly, this is a very high temperature. It's this thermocouple module is here. It is minus 200 degrees Celsius to 1050 degrees Celsius. It is actually. It's chromal and aluminum, right? These are two bimetal, right? Alloys used in this. You see here, this the thermocouple is ranging from 1000 to minus 200 to 1050 degrees Celsius. It can vary. Are you able to see the values here? It is minus 6 millivolt to minus plus 33.2 millivolt. See, what is the total variation in this total thermocouple signal for the temperature variation? It is less than it's a 40 millivolts, right? See, 40 millivolt signal is for the range of over 1000 degrees Celsius, right? So the acquisition module should be very, very robust. Actually, here you see here, suppose if the cable is without a shield, the thermocouple will pick up some EMI/MC, right? Other environmental signal it will pick up. That's all gone. See, suppose 6 millivolts of signal it is picking up. This cable picks up. What will happen? Your measurement will have 200 degrees Celsius error. You got it, no? So that is this is mainly for you need to have a shield, proper shield in the cable, and otherwise you need to go for proper twisted cabling to prevent the signals being picked up by this kind of cables, right? Now, this if you see the thermocouple, this variation, right? See, this is the response time of a thermocouple. See, for example, it has to pick up this 100% of its values, right? It takes around 1 to 2 seconds. Also, this thermocouple depends on the variation depends on your diameter of the sensor. Lower the diameter, response time will be less, right? If the thermocouple dia is more, then it to reach maybe 5 seconds it will take. So once we were asked to put a thermocouple for a missile firing, the effect on the wing, right, on the belly of the aircraft. So, but the thermocouple response time is 2 seconds, but the missile will go in 20 milliseconds, 30 milliseconds, right? So it can never pick up that kind of temperature effect on the wing, right? So we need to think of different way of testing, instrumenting that, right? So this response time is a function of diameter of the sensor, and it takes time. See, it has to reach 100%, then there is a correct value. It takes some 2 to 3 seconds, right? So if that time is not a critical for us, then we can possibly depend on this kind of sensors. See, this is a particular K-type thermocouple data acquisition module. See, you can see a thermocouple installation on the aircraft. See here, this it is basically inside the engine. You see It is mounted with kind of high temperature, some kind of sealant, right? This is the sensing point, right? And it is going, this thermocouple reaches the other two ends of this thermocouple along with the shield reaches our data acquisition module, right? You see here, this has got, this is 16 channel thermocouple module, right? See here, it is analog plus minus and ground, right? So plus minus comes, analog plus minus comes here. So you know that I'm going to occur only maximum of 40 millivolt signal, right? So this is the shield for that, right? So, but in thermocouple, there is here, this same path will be, it's a block diagram only. Like this, another 14 will be there. This kind of channel path, bottom if you see, there will be 14 kind of paths, analog inputs will be there, right? After that, 15th point, sorry, 15 will be there, 16th is your RTD. You can put one RTD small sensor is put on the connector itself. Why do we put this RTD in the connector? See, thermocouple is works on the basis of what? Seebeck effect, right? So two dissimilar metals, when you put two junctions are maintained at two different temperatures, EMF is induced, right? Voltage is induced, millivolt is induced, right? So here, this is mainly for RTD. One another type of sensor is put to find out the junction temperature. This is called, normally in the thermocouple term, this is called cold junction, right? Because the junction where it has to be measured in the engine is called as the hot junction or the junction measurement point, right? So this cold junction, when this all this connector of same temperature, this temperature should be known, right? So there is the equation for cold junction compensation. Then this temperature exactly, this millivolt will be mapped to the temperature with the cold junction compensation value, right? So this is the function of this module, right? So a sample case I have taken. When we record, one second, what's the time? Okay. When we record thousands of parameters along with the video, right? Suppose an incident happens in the aircraft, right? So how will you analyze the case? Or you want to analyze the critical weapon release events, right? How will you analyze the event with respect to a common time, right? Timestamp is very, very important in our flight test instrumentation, right? So time is critical when it comes to data. It is means of correlating data with the event, right? Every parameters which is acquired, for example, a parameter is acquired at 1,000 samples per second, right? That kind of your time stamping of the parameter is very, very critical. Otherwise, you can't compare with the other parameter, right? So video event can be played back with your temperature event, or video event can be played back with the flight control event, how the pilot is giving input, how the aircraft is responding, how the missile is getting released, how the fuel line is getting connected. All these things needs to be compared precisely with time to have a proper analysis, right? So this kind of time stamping of video, events, data, everything is required. So time is critical parameter when it comes to data analysis and analyzing the data precisely. So you imagine thousands of parameters without a reference, you won't be able to analyze it, right? So time analysis is so critical. So each parameter, this data acquisition system will have a time. So telemetry system we follow. Before that, I want to introduce you to the standard. See, IRIG-B. IRIG is Inter-Range Instrumentation Group. This is comes under RCC, Range Commander Council. Say, for example, this is a big council is there, RCC. They dictate the terms, right? They form the standards, right? This NASA, everyone is involved. All the range people who test the missiles, launch vehicle, or all people are part of this RCC. They follow this IRIG-B time. Right? Our telemetry, we follow this IRIG-B. This is a modulated time. Time is small. See, This IRIG-B carries this IRIG-B signal is synchronized with GPS. GPS has got 1 PPS pulse, which is very, very precise in accuracy of plus or minus 5 nanoseconds. And this IRIG-B time plus this 1 PPS helps us to make our data acquisition system to timestamp the parameters very precisely. This I have shown a picture of a onboard TCG, a time code generator, IRIG-B time code generator. It gives the time to various systems, mainly data acquisition system, and some outputs go to recording system also. So everywhere it is precisely, some goes to video recorders, right? So like that. So every single thing is timestamped precisely to get the proper data, complex data, right? See this time word format or like this. It is coming in this 16-bit 3 words coming. See, one is telling about the day, hour, minute, and second. The second is up to 0.10 second. Third word is carrying you until microsecond. So this time is you get the time to the accuracy of 1 microsecond in this, right? So after getting the time, we need to from the UTC time, we need to our 5.5 hours delay we need to take care, right? So here the time, you know that your GMT, has got a variation from 7.5 degree longitude to east to another 7.5 degree east and west. So if we take 0 degree longitude, this side 7.5 and this side 7.5, we have the same time, correct? No. So the same this this is totally 15 degree, right? This is 7.5, 7.15 degrees. Okay. So all longitude corresponds to time. See, that's how you take UTC time. Our every time we vary in our time. Right? So now I'll take a case of a weapon instrumentation. I told already one video about that. I showed a picture of the weapon which is instrumented, how it is captured in the aircraft. So you can see this is a pod which is carrying the cameras, right? Sometimes in this case, in this aircraft, there are, so you can see one camera at the near the engine, this is the rightmost. You can see one camera mounted near the engine exhaust, and these are all the weapon pods in the aircraft, right? So here, in this outboard station, there is a pod in which the cameras are mounted. You can see 2 cameras are mounted, which are pointing to the weapon to capture some event. It may be release of your bombs or anything. These cameras are focused to capture those things, right? You can see this on your left side that bombs are having a lot of stickers, right, to quantify the data. Right. Why do we do this? Before releasing the bomb from the aircraft, a lot of validation is done by CFD models. There's a huge amount of complex algorithms and very, very intensive algorithms are used for evaluating the weapon release characteristics of an aircraft, right? So this model shows if the aircraft is going at 1.2 Mach speed, and if the weapon is released at an altitude of 10 kilometers, this has to go like this. That's a simulation study, right? How do you establish that in flight test? We need to have this kind of systems, cameras, high-speed imaging system where your weapon parameters are analyzed, right? Here, you see here, this is the fixed pylon. This is the bomb which is getting released. You can see the bomb is getting released. The piston is pushing the bomb down, right? So this high-speed camera gives the 200 to 1000 frames per second imaging it can do, and it can give you the 6 of parameters. So yeah, 3 attitudes, that is roll, pitch, and yaw, and also the displacement X, Y, Z. Displacement of the bomb with respect to your pylon in the fixed part of the aircraft. Now, coming to the data. Right. Now we have seen the sensors, then how we acquire the data in various boards. Say for example, typically in the aircraft, some proven aircraft will have only 2 data acquisition systems. Some will have 10 or 12 data acquisition system. Even commercial aircraft will have flight testing phase. It will have more than 50 or 60 data acquisition systems. Right. All data acquisition system acquires the data. Right. And it has to be, some will have to be transmitted to the ground station. So when it comes, we have to plan the sampling rate and how we have to send the data through a PCM bit stream. It's a serial stream of data, right? So we follow IRIG 106 chapter 4 for our PCM stream. This is standard used, right? This standard says how a PCM frame should be, what and all the parameters in a PCM frame, how it gives a guideline for your PCM stream and how it should be transmitted, how it should be timestamped. All these things are defined in this standards, right? And finally, it comes to what is the bit rate, how much bit rate is required for you. Okay, so this is our responsibility. Say, for example, if they say 1,000 sensors you have to connect, okay, and some 8 mil bus avionics buses you have to connect, some 4 flight control system you connect. So total parameters will be around 10,000 parameters that the data acquisition systems are allowed to collect. Right? How is it going to collect? Right. So you have a parameter called bit rate is very important. See, that is to optimize the transmission. Everything, if you want to transmit, it's very difficult, right? So nowadays, the schemes have come to transmit more and more information, but everything is very difficult, right? So you have limitations, regulations, regulatory limitations are there. We have limited bandwidth to transmit. All these things are linked to each other, right? So bitrate is very important. Now coming to a sample case, I have taken a PCM bitmap structure, right? So you have frame sync. See, in a frame, PCM frame, this is a PCM frame, right? So you have first is a sync pattern. We call FS1 and FS2 or sync pattern. Then you have SFID, that is subframe ID. Then comes the time. I told you the IRIC time. 3 words are put here, right? Then the data, right? The data, this goes to as much as your frame requirement is there, right? So this is how we call it as one minor frame, right? So if you have say for example, n number of minor frames, we call it as major frame, right? The entire thing. So we have to decide on, based on your sampling rate, how many major frames in a second we need to transmit, right? One major frame has got multiple minor frames. Every minor frame starts with a sync word and SFID. Say for example, SFID is starting from 1, right? If there are 32 minor frames, SFID will go from 1 to 32, and your sync word will be always there. This is mainly, it's transmitted in every minor frame because it has to be get back. You have to get back. Okay, frame synchronizer and the receiver will take the sync word and decommutate the PCM frame, right? So this sync words are used, right? This is standard used everywhere where the telemetry is used. Most of the similar standards, right? So you have sync word, SFID, then time, then the data. This data can be video or audio, analog video or temperature signals or your bus signals, bus data. Mailbus 1553 has got huge amount of data which is flowing in the mailbus. Those data also can be put onto the frame based on some scheme defined by the IRIG standards, right? Now you take I'll just take a case of SFID. To simplify this, we have not shown this SFID, sync pattern here. Now all subframes are having SFID data, different data are put. See, now there are 2 types of PCM commutation. Commutation means what? Taking the data, encoding the data into digital format and putting onto the PCM frame, that is PCM commutation. We call it as commutation, PCM commutation, encoding or PCM commutation, right? So encoding of the data in this frame, you have data, various data. Say for example, data 1. Say for example, this is one parameter. Data 6 is placed like this. But we see here data 1 in the subframe itself, multiple times it is coming. Here in the SFID, in the first subframe, it is coming in 2 places, right? So such parameters which has got high sampling rate, which is repeating more times in subframes, are called as super commutated words, right? Suppose some words are occurring in water. Data 2, if you take, it is coming only one time. It is called subcommutated, right? Subcommutated, a minor frame word, right? So these are all dumped into, okay, this we use super commutated and subcommutated. We'll take that with those two, okay. Now I'll take an example of a PCM frame. See, in this frame, there are some information is put: accelerometer, strain gauge, and temperature, right? So this accelerometer data is what? Vibration data coming from the aircraft. Okay, they are put in A1. Right? See, accelerometer or put as A1 parameters are put in all subframes 1, right? Here 14th, again it is repeating in 8th, 14th. So these are all accelerometer data or what? Super commutated data. See, whereas temperature, you see T, you see here temperature data. Temperature data is water. Here you have in this frame, it is only one time it is coming T1, right? So it is subcommutated data, right? So this is a simple example of that, right? So say for example, say we have to decide the PCM map structure. Let us say A3 parameter. A3 parameter is coming in 4th position in all the subframes and 10th position in the subframe 16, 22. You can see the distance between this are equal, maintained. Okay, because samples are taken and it should be placed so that the integrity of the data will be maintained, right? So A3 is placed in 4, 10 and 4, 10, 16 and 22. Okay, equal places. So it's a super commutated word. So our requirement is what? Suppose you should have a minimum sampling rate of 2115 samples per second. That's a plan given. So I need to maintain 2115 samples per second. So this this frame of 12 minor frames of 24 words each, how many times it has to come? Right, in a second. In a second, this frame, how many times it has to come? That we have to work out. See, 2115 samples per second into major frame. In one major frame, how many times it is coming? Say, for example, this how many times A3 is coming in this? Almost how much? 12, 48 times it is coming, right? Major frame for 48 samples, right? So if you say it is coming to 44 major frames per second, you have to work out, right? Say, for example, samples per second is given, right? In a major frame, 48 samples are there, right? So how many major frames per second, if you want to calculate, you have to multiply this to this thing, right? So 2115 samples per second, major, this is the, you will get into 44 major frame per second, you have to transmit to get the signal. You got it? So in a second, you should have 44 major frames of PCM frame needs to be transmitted to achieve your 2115 samples per second minimum, right? So you approximate to a nearby sample value and remaining you can leave this place free, right? So further example of putting all the parameters, right? So that's the thing. So coming to all these things, 45 major frames into 12 minor frames into 24 words per minor frame into 12 bits. Suppose you take a case of 12-bit word, then it is normally we take 16-bit. In this example, it is taken 12-bit. So you have a data rate of what? A sample as a case, it is 160 kilo samples per second is your bit rate. But normally it will be huge. As example, we are telling it will be in the order of some 2 Mbps or more for the data itself. Video, when you want to put, it will be more than 6-7 Mbps. Okay. Now we have got how to arrive at a data rate, right? So we acquire the signal and put it onto the PCM frame, and we have decided the data rate. Now we need to transmit that, right? What we need, the channel bandwidth is, telemetry bandwidth is known. This is given by our WPC, Wireless Planning Commission, gives us the bandwidth. We have to buy the carrier frequencies, and with they come with a bandwidth. Say for example, I'm being allotted with 4 carrier frequencies. Then each they will give it a bandwidth. Okay, so bandwidth means say some I'll take for data 3 megahertz bandwidth, some I'll procure, and I want to transmit video, I need to have 13 megahertz bandwidth, right? Like that, 20 megahertz bandwidth, whatever it is. So this bandwidth has to be decided based on our requirement, right? And I should have a license to transmit. Okay. So various types of solid state recorders. Now it comes to a recorder. Before going to the further transmission type, we will take recorders. So how these recorders or solid state recorders, right? So it will be in an accessible place in the aircraft. The panel can be, when after the aircraft lands, the panel can be opened and the cartridge, where solid state recorder cartridge can be removed, and you can put it in any playback station. We can play the data, extract the data, segregate the data into engineering units, and distribute to various designers, right? So aircraft data, when the aircraft lands, test aircraft lands, we have huge GBs of data, right? Some 30-40 GBs of data will be there per flight. So this data needs to be sent to various design groups, right? So we'll put in the common jukebox, various labs, HAL, NAL, all people will access the data, they analyze the same day, and they clear for the next flight, right? So this is how it works. So these recorders are very critical. This recorders records everything in the aircraft, right? All the bus, MIL bus, 1553 bus, avionics buses completely, this flight control buses lines completely, then all the sensor data, everything will be recorded in the solid state recorder with a common timestamp, right? So after the flight, the cartridge will be removed and data will be extracted into engineering unit. It will be distributed to various groups. Then after recorder, now is another line's transmitter, right? When you come to transmitter, what are the types of signals we have? We have NRZL signal, then we have bifacial signal, right? Various cases we use based on different, based on the requirement, we select the signaling, baseband signaling, NRZL or bifacial or something like that, right? See, there are different types of modulation schemes. PCM FM is there, SO QPSK, then advanced modulation. Why different types of modulation schemes are required? PCM FM occupies more bandwidth comparatively, even though it is a very robust, but it is a bandwidth hungry type of transmission, right? Little bit we can optimize when you go for this kind of modulation. SO QPS, shaped, offset, QPSK, and other CPM have not started using, right? So this are the further the bandwidth is reduced for the same data, right? See, when you want to transmit, we need to have a band of operation, that in this band only we can have why these standards are there, bands are there. This is to make the manufacturers of transmitter and receivers to follow that particular band. Suppose I am working on L band or S band, right? I will be in the this thing, we will have a transmitter available in the band, receivers available in the band, right? This is the band which we use 1435 MHz to 1525 MHz. In this band, we will have multiple carriers, which licensed carriers, which we will be using. The carrier which we use for our flight test, nobody else can use, right? That is purchased by us with some band, right? So similarly, this S band also we use, and we are slowly migrating to C band also, because a lot of mobile operators have come very close to this S band. We need to migrate to C band. Okay. This basically a transmission chain. When you come to a transmission chain, basically a video transmitter is shown here, data or video, the L band case. Okay. So when you put L band, what is the major effect on L band? We have a GPS receiver in the aircraft. Okay. So GPS receiver is what? Basically, it is 1575 Macet. When our transmitter of 8 watt or 15 watt is being pumped out of our transmitter outside, so we will kill the signals, very small signals of GPS, right? So we go for this kind of notch filters, right? Notch filters will attenuate. It's like a comb structure, right? It will attenuate only that GPS band, right? It will give an attenuation of around 60 to 85 dB attenuation. It will give to our GPS band. Then it goes to top and bottom antenna of the aircraft with a passive power divider. You can see the pictures. I put some pictures of a transmitter and splitter, right? Power divider, right? And some antenna used for transmission, right? The important term or a term which we when it comes for analysis of the performance of the transmission system is bit error rate, BER. Right? What is this bit error rate? It's the number of bits received in error by total number of bits transmitted. Right? It's called bit error rate. Right? Normally we operate for this thing. Say for example, 1 in 10 power -5. That means our BER is 10 power -5 means it is 1 bit error in 1 million bits, right? So this is the my performance definition. I need that much of bit error BER required for my transmission. 1 into BER of 10 power -5. That means 1 bit can go wrong in 1 million bit. Okay. Basically, there are this bit error rate and the signal to noise ratio, or EV over NOT, gives the or used for evaluating the performance of the telemetry system, right? What is signal to noise ratio? What is your signal power and to the noise power? How much noise is there in our system and how much your carrier or modulated carrier, how much power, right? So that is called SNR. Now, I put a PCM FM bifacial signals also. Bifacial signal, the advantages you have bit transition in every bit. There is a transition in every bit duration. Okay. So this is basically the as per standard, we should have a deviation of carrier up to 0.65 times of the bit rate. Okay. Say for example, 1 Mbps bit stream, you should have a maximum deviation of 650. That means what? 650 kilohertz into 2 is your bandwidth, right? That much the carrier will be deviated. Right. Now, when you come to analyzing the system, right? So you have the bit error rate to SNR, signal to noise ratio, right? IF SNR in bandwidth. Why we are taking IF SNR? It is mainly the receiver you have when the signals are RF signals are received, it will be pushed into IF. It's a down conversion, right? In the IF band, okay. In the IF band, what is the this SNR in this IF band? Okay, that means say for example, I want to achieve 10 power -5 bit error rate, right? In this graph, this is the graph. This is standard graph. In this, you see, I need to have a signal to noise ratio of 14.8 dB, right? 14.8 dB SNR is there only. I will be able to achieve 10 power -5 bit error rate. It's optimum, right? Suppose my signal levels are going lesser and lesser, your noise, your bit errors will be becoming more and more, right? So we should always, for a better telemetry coverage for PCM FM, normal PCM FM, we should have this is a standard. This 10 power -5, you should have your say signal to noise ratio of 14.8 dB. Okay. I'll take a simple case of a link budget. It's I've taken a simple PCM FM case where I have a 3-meter dish antenna, right? I need to track a target aircraft up to 200 kilometers, right? My IF bandwidth, I told you, the signals are coming to IF. Everything we talk in terms of IF bandwidth. So, say for example, I am concerned about a video. Okay, normal analog video. So I need to have a bandwidth of 13 megahertz, right? So I have a signal to noise ratio of 20 dB I have taken. That is the thing. Because I have to achieve 10 power minus 5, I have what? 14.8. So I need to have a cushioning. So I am keeping 20 as my 5 dB cushion power and transmitted power of 8 watts, right? See, you here, transmitter is there. These are the key parameters which we need to always remember. This is EARP is effective isotropic radiated power. It is the product of this power, transmitting power and gain of your transmitting antenna and your loss between the antenna and the transmitter cable. That is CLT, right? Then comes the path loss. Path loss is a function of what? R is the range and lambda is function of what? C by F, your transmit frequency. So path loss depends on your range and your frequency. Whereas EARP depends on transmitting and receiving antenna gain and the loss, right? Then comes the received. How much signal is ultimately received is the PT, GT, or GR. That is transmit power, gain of transmit antenna, gain of receiver antenna, and path loss divided by path loss, right? Now let us take a simple case. Here, a case of 8 watt I need to transmit, right? So I'm multiplying here with 1000 because it's a dBm I'm taking as a reference, because most of the receivers we talk in terms of dBm, that is dB with respect to 1 milliwatt, right? So 1000 is multiplied. Take the convert. Then 0.5 cable loss and your transmit antenna gain is 3. Why we are going for logarithmic scale? Here when we go for logarithmic scale, it is easy. Everything you can take in the terms of dB, just you can add, right? So here, this is standard because it's a huge scale. So we need to go for logarithmic because of the wide range of frequency also, right? Now EARP in this case is taken as 35 dB, right? 8 watt transmitter, cable loss between transmitter is the 0.05 and antenna gain is 3 dBi. So we have EARP of what? 35 dB. Then the path loss. See, I have decided the range as 200 kilometers. So if you put 200 here and lambda C by F, if you put, you have totally 141 dB signal will be lost on the path, right? So here, so EARP minus path loss, what is the signal which we are getting at the input? It is around 1.59, 1.5.9 dBm signal only will reach here after when the aircraft is at the distance of 200 kilometers. So when in the antenna, the feed, this much of signal is only reaching. In the feed, when you see, it has got a band pass filter and LNA will be there in the feed. Low noise amplifier. This is very, very critical in the complete tracking chain. It has got very good noise performance and good linearity. All those things it should be there. And this is the feed. Then the pedestal, it's a rotating part. The antenna has to move in azimuth 360 degree and elevation 90 degree. Okay, so it has got two moving part. One is the elevation motor, and that pedestal will move in both elevation and azimuth, and it has got a rotary joint because the cable will have to go through the rotary portions. So it is a rotary joints are there. So everywhere the loss will be there. Okay, so here when you come to all the losses are defined in terms of what? Noise, temperature, and noise figures. Mainly the noise in the system. See, we talked about the signal. The noise in the system will be characterized by noise temperature. It is not a physical temperature. It is the effect of temperature on noise. Okay, even though it is talked in terms of Kelvin. Okay, it is quantified in terms of temperature, but it is the effect of noise in the system, right? So I think less time to cover, right? Only 10 minutes to go. Okay, I'll just go through a little faster. Right. This is the noise temperature. It is given. If your tracking system manufacturers will give a system temperature, right? So G bar T, the gain of the system over the system noise temperature, is the main performance indicator of a basic tracking system. suppose a tracking system is to be defined, this G bar T is the main parameter. Gain to system noise temperature, G bar T. G over T or G bar T is the main parameter which we have to consider in the calculation of the link. Right. So now when you come to the system, right. So LNA, first portion is LNA, I said it has got a 35 dB of gain, this LNA, and 0.5 noise figure, and the noise temperature is what? 36.7, right? Gain of the next, here the two gain portions are there, one multicoupler. After the pedestal, the signal goes to multicoupler where it is given to different receivers, right? So this multicoupler takes two this RF inputs and distributes to various receivers, right? So this is a multicoupler. It has got a gain also. And the system has got lot of losses. Okay, each cable, each path has got losses, right? The losses are consolidated here, and the receiver has got a noise figure. Okay, at 12 dB, right? So these are all used for computing your link. See, if you take a signal, this is basically the noise floor. If you take the spectrum of the signal, this is the noise floor, right? When the RF signal comes, we can first monitor this, right? So it is around 110 dBm noise is there in the noise floor. This is called noise floor. And theoretically, we can establish the noise floor with a IF bandwidth, right? IF bandwidth, say for example, this is basically noise floor is, when it comes to the receiver, we will use this IF bandwidth. Basically, the noise is what? Noise floor is KTB. You know this K is Boltzmann constant. T is the temperature normally taken as 295 Kelvin, and B is the bandwidth, right? So your noise floor in this case is minus 104 dBm, right? You can see this noise floor 104 dBm, right? But the noise floor, which initial thing, when it goes to the receiver will show different noise floor for different IF bandwidth when you set. Okay, so higher the bandwidth, more the higher the noise floor. It is bad, right? So suppose if the interference is there, then also noise floor will keep going up, right? I can show you a simple receiver, what we use, right? See here, it is a L band, one signal carrier is selected, 3 MHz IF bandwidth is selected. So here you see the noise floor is minus 93 dBm it's showing. Whereas here 13 MHz is set, you can see the noise floor is around minus 87 dBm. So noise floor is becoming bad when the IF bandwidth is higher. Okay, that means what? When we transmit that kind of high bandwidth signal, you need to have margin well above that, right? Signal to noise ratio, right? Now, this is another system noise temperature. It's antenna. Designers will give you this antenna temperature and system temperature. This is basically computed with simple losses and gains of the system, right? Oh, system noise temperature is what? Multicoupler, this all this noise temperature in the multicoupler, the gain of LNA plus the loss in the line plus what? The receiver noise, then this LNA gain again. Like that, any number of cascaded channel, this formula will keep going up. Finally, it will end up as a system temperature. Okay, one temperature, one value of T, which is contributed by the noise and losses in the system, right? Now let us come to the receiver gain. The receiving antenna gain is around 30 dB. So totally the noise, total system noise plus antenna, everything together, you have 212 Kelvin. So noise floor I told it is 104 dBm. Okay, I told you noise floor here. Here, see, noise floor is a function of your bandwidth, the Boltzmann constant, and the temperature, all logarithmic values. Okay, 295 Kelvin, and this is the Boltzmann constant, and this is the bandwidth. So it is 10 log KTB is the noise floor of the system, right? This noise floor is based on your IF bandwidth, right? Now, when you come to telemetry link budget, the signal which is flux density of the signal which is coming to the receiver chain, and the G bar T is, we have calculated G bar T is 6.1 for this antenna. So since it's a 3 meter big dish, it has got a 6.1. A small antenna, we can even, it will be very 0.5 G bar T, 1 G bar T, like that we'll get. Okay. Signal to noise ratio, we are getting, I'll come to that link budget on simple calculation issue. We have time. See, when it comes to the 3-meter antenna, I'm having a simple case of 1.5 transmit frequency and range is 200 kilometers. And free space loss is what? 141 dB and transmit power is 8 watt. And the loss, then the transmit antenna gain is -3 dBi. And you have EIRP, we don't know, isotropic radiated power, it is 35 dB. It's not dBm, it is dB. Okay, dBm, okay. Power is in dBm, right? And the flux density is minus 105.96. That means flux density is what? F11 minus F6. F11 is what? EIRP minus what? F6 is free space loss. Okay, this gives this value. Okay. Then the receive antenna gain is around 30 dBi. Then antenna temperature is given, ambient temperature is 295. Then all the losses in the system. Then comes the calculated G bar T value of, I have shown all the formulas. You arrive at G bar T of 6 value. That is a performance index of this receiving system, right? And for 200 kilometers, it is calculated to be 27 dB SNR. Okay, when the aircraft is at 200 kilometers, we have 27 dB SNR, where our requirement is 20 dB for achieving bit error rate of 10 power minus 5, right? So we have how much margin? 7 dB margin. So 27 minus 20 here, we are getting 7 dB margin even at the distance of 200 kilometers. And the aircraft is at 200 kilometers, still we will be able to achieve the bit error rate of 10 into 10 power minus 5. Okay. They're coming to ground station. I don't know whether I have time for a ground station. Okay. This is basically a tracking system, receivers, and we have a displays in the ground station. And we have communication system. This is a manned aircraft, no? So we have intercom system where the test director can communicate to the pilot. And we have PCM decommutation system. The data which is encoded on the aircraft, it is getting decommutated here. We have a time reference and we have vibration real-time analysis system, then ground recording and playback systems, and the data again recorded on the ground. That is a real-time data, right? See, this is basically our antenna system, the ground station, where the multiple receivers are there, multi-couplers are there, and your tracking systems or antenna control systems are there, right? So we have various type of telemetry stations, right? Here is a test director sits and communicates with the pilot. This is a small station where we take it to the weapon ranges, right? You have different types of stations. Even we have portable station which we airlift with the different types of Air Force aircraft will take this and go to the place where we test the systems, right? This is basically a system which we have in Goa. This is a ground telemetry system we have in Bangalore, Goa, a big ground stations, right? Then comes the data. Data has to be recorded and processed for further it should be given, right? See, any input in the aircraft, it has to be come in real time, the data. And we should have a proper situational awareness. Say, for example, a gearbox system. When you monitor, you see here the inlet outlet pressure is being monitored, right? And you can see all the temperature and everything is monitored. It's a simple system. Complex system will have multiple parameters. You see here the aircraft position in the flying sector. It is coming in the map. So the test director can monitor where the aircraft is there and how much distance to your base. All these things comes in this situational awareness points, right, in the ground systems. Okay, if you have time, I can go for some more slides. Otherwise, I will close now. Shall I close now? I have some more slides. Shall I close now or can I go for another 5 more minutes?
Sir, you can go for 5 more minutes, sir.
5 more minutes I can go. Okay. I'll take a case of airborne separation inertial system, a telemetry kit, a sample case, where the requirement given to us was to compute the quantitative interbomb separation, which cannot be measured basically. It's very tough. How when the bombs are 4, 5 bombs are released simultaneously, how will you measure the bomb? See, when the bombs, suppose the aircraft is going at high speed and releases 5 bombs together. Why 5 bombs has to be released simultaneously? Suppose you want to destroy a runway, you want to destroy a particular building. So we definitely want to destroy it. All the bombs should fall very close to each other so that the destruction will be more. See, so but when we are releasing the bombs together, very with a short interval of time, the bombs can hit each other, right? So we were asked to measure the interbomb separation. So we have developed a small telemetry kit. This is the bomb fuse in the bomb, right? Rear side of the bomb, right? You can see the bomb rear side. We put our telemetry kit inside. This telemetry kit has got a PCM10 inertial measurement unit where your accelerometers, 3 accelerometers, X, Y, Z accelerometers and rate gyro circuited. And you have a transmitter to transmit the data to the rear side. You have the, see this bomb tail. This is the tail of the bomb where we attach the conformal antenna, right? The aircraft we use blade antenna. It has got a downward pattern, right? To receive the antenna data from the real time, because the data, because we cannot record, because the bomb will get destroyed after releasing, right? So we have to capture the data to find out the interbomb separation, bomb trajectory, all those things, right? This is the type of data which we received from these bombs. And you see here, before going that, we are going to the setup, we have done a lot of ground things so that the sensor works properly. Then we have gone for a captive flights. So the data is matching with our aircraft sensors. Then we went for the drop, right? See this, in this 2 bombs are instrumented with this kind of instrumentation. You can see the interbomb separation is clearly captured. Okay. Okay, thank you.
Thank you, sir. On behalf of Marthanda College of Engineering and Technology, it is my great privilege to express my sincere thanks to Sri David Livingston, Group Director, Aeronautical Development Agency, Bangalore, for his valuable contributions. His valuable insight on the topic flight test instrumentations was truly inspiring and motivating. We deeply appreciate the ideas you have shared with us today. Let's all make this opportunity to learn, grow, and collaborate. Thank you, sir.
Thank you very much to all of you.
Now, I hand over the section to Dr. R. Bibin Bose, Assistant Professor, Department of Electrical and Electronics Engineering, to welcome the resource person in the next section.
Thank you.
Thank you, sir.
Okay, thank you, ma'am. Hello, audible?
Yes, yes.
Okay. Oh, good evening, everyone presented here. On behalf of Macet College of Engineering and Technology, it is our pleasure to welcome our esteemed resource person, Dr. P. Sasikumar, to today's Macet Atal Fdp Day 3, Session 6. The topic is Role of Rockets in Space Exploration. We are honored to have Dr. P. Sasikumar with us, graciously accepted our invitation to share their experts and knowledge with us, who has scientist, engineer in Vikram Sarabhai Space Center, ISRO Trivandrum, since 2004, who has completed doctorate in IITM Chennai. He has 20 years of experience in quality assurance of launch vehicle composite and heading the launch vehicle and satellite composite processing team, who has published a lot of books in English. That's Sky Riders, your goal within your reach and quality resolution in practice, rocket science, etc. And some other books published in Tamil, கைத்தறியும் கணிப்பொறியும், நில்கவனி அறிந்துகொள், விண்ணுறுதி, வனவாசிகள், etc. We look forward to a simulating and informative section. Welcome you, sir. And also welcome all other participants from various colleges. Now take over the section, sir. Sir, please take over the section, sir.
Okay, good evening to one and all. Hope I am audible. Can you someone confirm?
Yeah, yes, you are audible.
Yes, sir, audible.
Okay, okay. Hope my slide also visible.
Yes, yes, yes.
Okay, okay. After a very lengthy class, I'm just taking. I will take a 1 hour. Then after that, we will have any question answer session. We will have. I'm not going on much on equations and all, but I try to explain in a layman language what is this rocket, how it's helpful in reaching to space. You may aware what are the space application. I will just touch upon types of rockets and their fuel, and then other than the regular satellite, what else this rocket is used to take satellite to the outer space and the deep space exploration and all. That is my idea. In the front page itself, I have put missile also, rocket also, from the first Goddard rocket also. So missile also part of the rocket, but we are going to discuss today on only about the launch vehicles only. So missile and rockets, missile and launch vehicles are subset of rockets. So today my focus fully on launch vehicle area. If anybody asking why we should supposed to go to space, now everyone knows the answer. So without satellite application, we cannot imagine our day-to-day life. If you go to the ATM, you want to take money, or if you want to watch any communication related televisions, even mobile also now, from the terrestrial network based mobile to satellite based mobile and communication, broadband, everything we are thinking about satellite. Some country they were already connected satellite based broadband connection and all. Then if you want to see that satellite usage of data, there we are plenty of satellite data we are using, not only for the agricultural purpose, even the city mapping and where you want to design a city, you want to map where the dam should be constructed, where the minerals are there. So like that, plenty of applications all are there. So these all are from the satellite data. For this, we have to take our satellite, put in a particular orbit. The role of rocket, if you simply tell, this is the vehicle. It takes either a spacecraft or space shuttle or whatever you can say. It is taking from the ground and taking to the required orbit, and it is placing in the required velocity. That is the role of this rockets. So rocket life will be like 10 minutes to 20 or 30 minutes. That's all, based on where it goes. Or sometimes the last stage will go some further. Then after that it will leave it. Then satellite or space capsule will take over and it will travel to the required distance, or it will be in the orbit. So how this rocket is designed and what are these challenges, what are the missions it is really doing, then is it really costly, why this technology is very complicated, those aspects only I'm going to talk about today. Say simple Newton third law you know very well. So what is for every action there is an equal and opposite reaction. If you fill a balloon with full of air and release the air from the small mouth, so when the air comes out, the reaction force will generate that try to push the balloon in some direction. If you put the balloon in the guided way in a rope, you tie it, then you do this, where the rope is there, along the rope it will travel. But the problem is when you want to lift the larger amount of mass, this air alone not sufficient. You can do the same exercise with the water also. You can pressurize the water and opening via small nozzle. So when water is comes out, the force will be generated that will push the rocket upwards. But when you go for a larger system, so this is not a possible. So how long you want, how much thrust you want, it should be decided. Accordingly, continuously the gases should be come out. There, storing a cold gas not the option. We have to go for a fuel based things. So what we'll call as propellant. So this propellant will be fired. So then this propellant will generate the huge amount of exhaust gas. So that exhaust gas will be uh, come out from the small opening called nozzle. So that will generate the thrust. So that will be used to your lift the rocket. This is a simple idea. If I simply fire the fuel, say here, whenever we term about rocket terms, we will talk about propellant. The propellant mean it is a combination of fuel and oxidizer. So we are going the out of atmosphere, there the no oxygen is exist. To fire any fuel, we need oxygen. So this oxygen also will be carried away. So this oxygen or the oxidizer which is produce the oxygen may be in the form of liquid or solid, whatever you can call. So all this combination we are calling as a propellant. If you simply fire a propellant and you will get one energy, but instead of that, once the fuel is propellant is fired, then you bring it to the you increase that via you can see this picture. So this is called we call as a D-level nozzle. So instead of directly expanding, you just compress it till it is reaching the Mach number of 1. Mach number of 1, you may know something like a 331 meter per second. It is for the normal, but here gases and all changing, it will be different. After that, if you expand, we can get the more energy. That is the concept. So if you put a nozzle, whatever energy we are getting by firing the propellant, that energy will be multiplied by a factor called thrust coefficient. This factor will vary from something like a 60 percentage to 75 percentage according to the design and all. So this is the concept. So here how the propellant, how it will be burnt, how long it will be burnt will be decided by a type of a rocket. Okay, we'll just see some history of this rocketry. Originally, people will tell when the Leonardo da Vinci has drawn the picture of a aeroplane or a flying object. So it was some 400 years back it was done, but no one was succeeded. Usually we come across this statement, but really the fact is the ecosystem to generate the engine to fly was not available. So Da Vinci was drawn a picture which is simulating the flapping bird. So flapping bird concept of flying element is still not succeeded. When almost like a 19th century middle or end, we found the crude oil. From the crude oil, end of the century only, we found that gasoline and the diesel. So when that was developed, then everybody was understood. Then petrol engine came and diesel engine came. It was very famous. Then everybody started using petrol. In 1900, America itself, more than 1,000 automobile companies were there. They were the like a startups. Everybody was trying to make a one moving element that is called automobile sector. So in that way only, Wright brothers also used this gasoline engine in 1903 and they were flown. So after this, so the same gasoline was attempted to make a rocket also. In that person, he was succeeded in that. So in 1926, he made a one liquid rocket. So that was flown. Okay. It rose to 41 feet. It went almost 184 feet. That is the range in 2.5 seconds. This was the first successful flown rocket which was used petrol as the fuel. You may aware the Second World War, Hitler was used the missile called V2. So that was originally used ethanol as a fuel. In the 25 percentage water was added. Then liquid oxygen was the oxidizer. So this is the initial. Then there was a breakthrough in this technology, the rocket equation. Selowski was found the rocket equation in 1897. Later it was published. So what he was telling is, so I will explain this part later. Say if you want to launch any satellite, there is a minimum velocity requirement is there. At what altitude you are there. So to keep that satellite in that altitude, we have to give a one minimum velocity. Why that velocity and I will come back. How this velocity can be given was explained by this rocket equation. If you know that initial mass and final mass and the exhaust velocity of a nozzle. So how much delta V can be put on this each system? That is the relation this was giving. Okay. So now you see, suppose effectively the exhaust velocity is like a 2 kilometer per second. Initial mass is 225. Then the final mass is 70 ton. So change of velocity, the delta V will be like a, something like a 2.335. How it will be useful and all I will cover later. Okay, somebody put a line on the slide, I think. If possible, admin can delete that line. Okay. So parallelly, this development was going on. Then people were working on how we have to reach space and how we can fire the engine like that. So many things were attempt was going on. In that, one notable person was Hermann Oberth. Okay, he was studying this concept. Then he was telling, if you want to go to the outer space, means from the out of Earth you want to go some other, we have to fire the satellite when it was near to the earth. That was his PhD finding. But that time this was not digested by the people. We were not aware about rocket, either rocket or satellite. So this his PhD thesis was rejected literally. In 1923, he published his findings, PhD thesis as a book, The Rocket into Interplanetary Space. So Oberth had so many students. In that, one of the students only, our Werner von Braun. So he was the team leader to develop the Saturn V rocket, which was used to take the human beings to the moon. Okay. So meanwhile, before this rocket equation was published, then there is one more person. He was in Russian space agency, that is called Sergei Korolev. So he also was developed so many rockets. But before that, how these two people are came, that history was so much interesting. Say 13th century, between the Mongolians and the Chinese, there was a war. In that war, the first time rocket was used. Then later, 1780s, that is the 18th century back, Tipu Sultan father Hyder Ali was started using this rocket. So he was using a rocket which is made up of a wooden blank. In the wooden blank inside, the gunpowder was filled. It was fired. So this process was watched by a 12-year-old Tipu Sultan. So he thought, say, why we should put a gunpowder on a wooden thing. So if you are filling at under pressure, so wooden hole filled thing, it will break. So if you want to increase the pressure, wooden block will not help. We will go to the metallic one. He changed that block into metallic one. So when metallic was there, he was filled under the high pressure. So due to the high pressure, this rocket was going a long distance and hitting. Basically, when enemies are coming, before they are attacking, it has to hit. That was a success. So there is a hint here. I will answer that hint later. So when 1780, 18th century last, this rocket was developed, still Hitler rocket in Second World War. So something like 140 years, why there is no rocket made? That was the question. So people might be curious how much far away this Tipu Sultan rocket went. It went something like a 1 kilometer to 1.5 kilometer only. But the Hitler rockets were traveled something like a 300 kilometer. So Second World War, Hitler understood the power of rocket. He developed their missile, so-called V2 missile. So this missile plenty he made almost like in 9 months period in the peak of the Second World War. He fired more than 3,000 missiles. After his death, after his Second World War, suddenly between the major power like Russia and America, who will capture this technology? The missile, they understood the power of rockets, basically missile, ballistic missile. Who can capture this power? There was a big fight between these two countries. So America started an operation called Operation Paperclip. So there they were hijacked more than 600 scientists. Not only that, the drawings and rocket parts, everything taken to their country. Some people who are all not part of that, they went to Russia. So like that only Werner von Braun went to America. He started his research there. Sergei Korolev, he was one of the person. Hitler thought he was delaying the rocket activity, so he was put in a jail during that time. So he went settled in Russia. So between 1947 to 57, so 1947 World Wars were over, Second World War was over, then the people were settled. 1957, the first launches happened. That I will come later. So between these two periods, Russia, what he did is, Sergei was in jail, so he was reproduced the missile which is made by Hitler with a slightly powerful called R7 missile. If you take a earth, so earth radius of the earth is something like a 12,700 kilometer diameter of the earth. So if you take a one full circumference of the earth, it will come around 40,000 kilometer. If you want to go from one place of the earth to any place of the earth, 20,000 kilometer is sufficient. If you have a missile which is can able to travel 20,000 kilometer, you can attack any country. That was the idea. Originally, they were developed like this only. But where will you test? Even though you are developing something, where will you test? That is the question. So that question, shall I, somebody is watching, shall I go back and come back to avoid this line, whatever it is come inside? Hope now line is gone. Okay, nice. Okay. So after that, what happened is, say they thought instead of going to the missile concept, if we're going directly to space, at any height we can go. Whatever the powerful rocket if you're making, this rocket can be tested. It can be go as high as possible. So like this only, the missile was transferred into the launch vehicle. That was the first point. But before that, what happened is, there are n number of launches were happened. So these launch and all we will call suborbital flight. When you fire a rocket or fire a launch vehicle, whatever you can call, it is, if it is not giving us sufficient energy to the satellite or whatever launched orbit to take a revolution of Earth, so it will simply fall. So Earth will attract, it will fall. So like that only ballistic missiles are working. You put a bomb in the rocket, you fire it, it will go to some altitude, say 1,000 kilometers. Then from the gravity, it will go there and hit the something. So like this, this called suborbital flight. Like this, thousands of suborbital flights were made. Even 1948, one monkey was sent, rat was sent, even dogs were sent. There are so many animals were sent between this period. Then here, after this, 1957. The literally the space Cold War was started from first to the 1957, where the Sputnik 1, October 4th of 1957, the first artificial satellite or man-made object which was made, and it was made orbit the Earth. That was the starting of the space era. Within 1 month, so the same rocket, whatever R7, they taken, they put on dog called Laika. So this dog was put in orbit, it also was orbiting. So whatever happened before that, all are suborbital. It will go to some height, just falling, like throwing a stone. But this is the first animal, it went and it is taken full round of Earth. But some sensors were put in their heart, how it is going and all. So based on that, within few 1 or 2 days, this dog was not alive. But this was that one. So 1961, Yuri Gagarin, he was the first person, he was orbited the Earth. Within 2 years, Valentina Tereshkova, first woman astronaut, she was orbited thing. So like that, the story was going. In the meantime, just 3 months before that Yuri Gagarin trip, John F. Kennedy has taken as a president of America. So he was thought as America is a powerful country. So why we should not competing with Russia? How Russia was leading? Yuri Gagarin also Russian, first woman also from Russia. Russia only developing. So he was so much unhappy with the way in which it was going. Though Alan Shepard went to May 5th, 1961, but it was a suborbital. He was not taken the flight. So in May 25th, the historical speech he was telling, so we will go to the moon. So he was putting a platform, or he is making the fight or race very tough, telling that say instead of going to pick off Everest, all those things and all. So when he was announcing, only 5 years before that only people went to pick off the Everest. So US put a platform where within 10 years, America will send the person to the moon. That was his thing. So he thought when he put a tough goal, then all other countries, especially Russia, will not be in the race. That was his idea. Okay, we will put a full stop here on history. So we will go back. If you ask vehicle, so launch vehicle is a one type of vehicle. There are n number of vehicles, different design of vehicles are available in market. You go, there are bus, lorry, then cargo, even car itself, petrol car, diesel car, all are there. But based on the requirements, say what power you want, what comfort you want, what is the pickup, distance. If you are going a race, you cannot take a nano car and go for the race. You have to take a race car. So it has to go at 200, 300 degree, kilometer per hour speed. So like that, rocket also based on the requirement, different rockets are there that we will see one by one, means launch vehicle. Similarly, fuel. See, if you take fuel, there are whatever the solid, liquid and gaseous, all three stages are possible. But in rocket, we never use gas. Instead of that, we will compress this gas at the low temperature and high pressure, we will make as a liquid. So only two propellant called solid and liquid only it is there. Then finally what did happen? So originally I told there is a balloon. Inside the balloon you are filling air. So the air will be released. So that is not sufficient. I will take a propellant. I will fire the propellant. So the fired propellant will come make a exhaust gas. That exhaust gas will be coming out of in the small opening in the nozzle. So that will generate the thrust. This is the idea I told. But however, say what we are doing is we are converting this thermal energy into the kinetic energy. That is the idea. But everywhere there is a efficiency. If you take any fuel you take, there is a energy content. We will call calorific value. So if you eat rice, so 1 kg of rice will give only 5 megajoule. If you take a full fruits, so doctor will tell if you want to reduce your overweight, you take a fruit. Means is your stomach will be full. So 1 full kg of any, so like a banana, if you take only 4 megajoule energy only you will get. But in case of you take any chocolates or like a butter type of item, fat item, it will have a 5 to 6 times higher energy. Similarly, so all fuel what we are using have a one calorific value. But this calorific value, how we are converting? When you are firing, then there is a loss to the walls of a rocket body called nozzles, or you can call the motor body. Then the residual kinetic energy, when it goes out, it will go out with some 1200, 1300 degrees centigrade temperature. Something not used like that, it will be there. So original energy what we are giving to the final energy, which is converted into kinetic energy, which is used to produce the thrust, will be 40 to 70%. That is the efficiency. Okay. So fuel I told liquid and solid. First we will see liquid. Say if you have to take a liquid, there are three type of liquid fuel we will tell. One is called earth storable, like our petrol and diesel. In the room temperature itself we can store it, like a hydrogen peroxide, nitric acid, nitrogen tetroxide, like that, and UDM. All these things will be there. But these all are toxic and reactive, then hypergolic. When both are touching itself, it will get fire, like this and all. Then cryogenic propellant, when you fire a propellant, so one will be at the lower temperature, that is called semi-cryogenic. In cryogenic, both fuel and oxidizer, both will be in cryogenic temperature. So cryogenic temperature means what? If the temperature is minus 150 degrees centigrade to minus 273 centigrade, if in between these temperature, if you store a propellant, both fuel and oxidizer, then both it is in this condition, we will call as a cryogenic propellant. Example is a liquid oxygen and liquid hydrogen. So liquid hydrogen stored at minus 253, liquid oxygen at minus 183. If any one of these in non-cryogenic temperature, then we call it as a semi-cryogenic. Example, if you take kerosene and LOX, there is a purified kerosene, this RP1 grade we will tell. So that in the room temperature, LOX is the other. If you take a methane also will be stored at minus 161. But however, it is out of cryo, we will call as a semi-cryogenic category only. See, there are reason, we are telling if you go to Mars, the methane is plenty available. So if you take LOX methane, we can get the fuel from Mars, like this, so many are there. So when next come to the solid propellant, so here fuel and oxidizer, both in the form of a solid. So we have to mix these two first. So how to mix? You take a one fuel, other is a oxidizer. Thoroughly mix both. Then mixing alone will not help that it will fire or the same ratio it will fire. For that we need a binder. Sometimes a binder itself will give us some fuel, but it may not be that order. Then additives we have to add at what speed I have to be fire and what is the burn rate I should get. All those things will be decided. So everything will be added. It will be mixed. Then this mixed thing will be cured in the oven. So we will cure in the oven. So we will solid motor will be ready. So if you take that, here the question is what is the fuel? See, unlike other case, now here fuel is some metallic elements only. That metallic element should have a metal should have a lesser density. That is the criteria. When you are taking to the rocket, the fuel weight should be less. So we are taking example. If you take aluminum, aluminum is a one of the best fuel. It will be 17 percentage aluminum will be there. To fire 17 percentage aluminum, we will take something like a 69 to 70 percentage of oxidizer called ammonium perchlorate. Then a small percentage of curator and all will be added. So that will be added. So finally everything mixed, it will be put in a oven, it will be fired. So now question will come, so how much fuel we are taking? Before understanding that story, we will get some small story about how our regular vehicles are there. If you take a cycle, say 20 kg cycle can take two people. Say 100 kg, two school boys it can take. So 20, cycle mass is 20, but it can take 100 kg of person. Means 5 times of it is mass it will take. If you take a car, so typically I given one car, 1058 it is a weight. So 5 people can sit 400, luggage is 800. So totally you see payload capacity is 35 percentage. So from the 500 percentage from cycle, it is becoming 35 percentage. If you take the aeroplane, so aeroplane will be like a 600 ton aeroplane will take 25 percentage as the payload. What we'll call as a payload is the whatever the weight or mass or people, whatever it is taking, that is the capability. But here you understand how rocket and these things works. Suppose you have a car, in that you have a petrol. Petrol is a fuel. To fire this petrol, you need a oxidizer or oxygen. But we are not paying any oxygen. So oxygen is plenty available in atmosphere. We are traveling in the earth. So earth surface. So earth surface has 21 percentage oxygen. So happily we are using, we are not paying anything to anyone. If you want to fire 1 kg of petrol, we need 14.5 kg of air. Suppose assume that the new rule comes today. Each person who's having a car, they should carry their own oxygen. There is no oxygen available in our area means. So if you are filling 10 kg of fuel, say if you return 35, assume 30. So I have to fill for 10 for 140 kg of air I supposed to fill. So if you 30 kg fuel, if I am filling, so 30 into 15 times something like a 450 kg I have to fill. Then drastically my payload will come down from 35 percentage to 10 percentage. So that is happens to rocket also, but in still in the higher order. Why that I will tell later. If you take a typical the Saturn rocket, which is taken the human beings to the moon, it was weighing something like a 3000 ton. In that first stage weight is 2219 ton. In the empty mass is only 130 ton. The second is 496, 123. So basically the mass of propellant which is carried by this rocket is something like a 90 percentage. So this is more or less will be common. So if suppose you assume that you are taking a bag, you are going to the tour, so you are taking a bag, so your bag weight is 1 kg, your luggage weight is 9 kg, it is effective bag. Suppose assume that you are taking a very heavy bag itself 5 kg, it can accommodate only 5 kg, means you are carrying 10 kg, but the net effective luggage what you are carrying only 5 kg. So that we will call mass ratio in rocket. The mass ratio supposed to be high, then only it will be good. It is, if it is low, it is not good. So all better design, it will be more than 90 percentage. The poor design, it will be something like a 80 to 90 percentage. So this is our GSLV rocket. So whatever the 100th rocket went last month. So here you see the total parts of a rocket it is given. So total structural mass. The structural mass means the element which is used to carry the propellant and control system, then interstages, then nozzles, whatever you can take, all these items called structural element that contribute something like a 9.5 percentage. The propellant mass is only 90 percentage. The payload, the satellite and whatever this rocket is taking to the required orbit, only 0.5 percentage. The total weight of this GSLV is 420 ton. Out of this 420 ton, only 2.5 ton only satellite mass. So why the reason is, so it has to carry more propellant, then effectively it has to design such that structure will be come down. Okay, now what is the energy it is required? So here the Newton cannonball experiment I will explain. Suppose I am giving a one stone to you or a iron ball. Can you throw it? If you throw it, it will fall only few meters. If I am asking some powerful person, say Olympic gold medalist, I am asking to throw that, so he will throw some more distance. Instead of that, I am asking you go to some height. From there you throw. Suppose fourth floor of a building or eighth floor of a building, then still it will take some more thing. But if you throwing a one particular velocity where, so this fellow is not falling on the earth, continuously taking the rotation around the earth, so that is the orbital velocity. So how it comes is, so Newton gravitation law what says is between the two objects like a satellite and the earth there is a attractional force is there. Then the second is the when you are launching this thing, there is a centripetal force will be there. Centrifugal, centripetal both will be there and minus opposite. If you throw the velocity which is equivalent to the Newton law of gravity, then the centripetal, then that is the velocity where it will not fall inside or it will not go away. It is simply to understand when my satellite to be near to the earth, say 150 kilometer, it has to travel at the speed of 7.8 kilometer per second. Suppose I am in 10,000 kilometer altitude, only 4.9 kilometer per second is sufficient. Okay. So if it is in the geostationary orbit, only per second 3 kilometer is sufficient. But how this comes? That is the next question. Suppose you are constructing a building. If your building is only is a 2-floor building. So 2 floor to pump the water from the ground to the second floor, we need some energy, some motor. Suppose mine is an apartment. My apartment is a 10-floor apartment. So 10th floor only my tank is there. If I want to pump to the 10th floor, so I need a more energy, that is called potential energy, what we will call. So when you go away from the earth, this potential energy will increase. That is the point number one. The second point is what I told is the kinetic energy. This is a potential energy, kinetic energy. So kinetic energy, when I am going above and above, the attraction force of the earth is coming down. So my rotational speed is come down, it comes down, but the net energy required will be increasing. That's why when 500 kilometer, the total energy required is 33 megajoule per kg, but 36,000 it is almost 50-60% higher, 57. So that is the thing. So you can see how potential energy from the hammer to we are giving, or when your cycle, when you are giving energy, when we are reaching a potential energy, that potential energy we are using coming down. So this much energy we have to give to the satellite to take in particular orbit. So that energy given by a rocket. So that's why the rocket is taking only the less thing. The second question is at what altitude or it will be putting a satellite? What is the orbit? So simply you can tell, I will tell it is a LEO orbit from 1000 kilometer from the earth. Medium earth orbit, it is still 20,000 kilometer. Geostationary orbit 35. Like that, there are different orbit we are telling. Where you are putting a satellite, accordingly coverage will be there. It is a simply understanding. But in addition to this, so there are so many other parameters is there. Whether are you putting a satellite in a circular orbit or a elliptical orbit, or your what is the equatorial, so okay, from the equatorial brand, what is the angle of inclination you are going to launch? If suppose my satellite supposed to be a pole to pole or sun synchronous orbit, every time, every second, 24 hours it has to face the sun, then how I am going to launch? All this maneuverability should be controlled by our rocket. So if you take example, so International Space Station put in orbital inclination of 51.6 degree. So why this inclination is important for this? It's very simple. So if you want to cover 90% of the world population, so we have to put this orbit. This is the orbit we are putting. Okay, why I'm see this is put at 405 kilometer. Okay, average in the altitude. Why I'm not putting nearby? When I put nearby, due to the gravity, so the decay will be very fast. At the fast rate, it will come down. If I am putting far away, the going and coming back distance will be more. So we are putting like that. So if you take a same Saturn 5 rocket, which has a 3,000 ton during liftoff, it is have a capability to launch 140 ton of payload to the LEO orbit. Say something like a 500 kilometer you can take. Means what? Only 4% of the total mass it can take it to the orbit. Suppose you tell that no, I want to GTO where that 36,000 kilometer I want to keep it. Then this will come down from 4% to 0.9%. No, I want to reach to the moon, still it will come down 0.5%. If you want to go to Mars landing, only 1.5%. The latest whatever Falcon Heavy you can take. So Falcon Heavy, the lift off mass something like 1,420 ton. It will take 63 ton to LEO, 26 ton to GTO, and Mars it is a 16 ton. There are riders are there. So these all are the world biggest rocket I have listed out. So Ariane 5 is there. If you take our biggest rocket LVM3, still it is half of the capacity of Ariane 5. So Ariane 5 also retired now. Saturn 5 was a proven one. So N1 was a rocket was designed by Russian to compete with this one, but unfortunately this was not succeeded. All two flights was failure. SLS one launch has happened. Second things and all going on. All other things are in trial. Starships, if it is operational, it will be the heaviest, both heaviest and most capable rocket in the history of rocketry that we can call. So 150 ton capacity. Okay. Now, so what are the stages this rocket is designed? So you can you say literally if you are speaking, many number of stages will be beneficial. Suppose you are climbing a mountain. So if you are taking a lunch box, dinner box, or food box, something like that. So after eating each snacks or the food, so we will not carry our waste dabba, whatever we are filled. We will throw the dabba to the dustbin and we'll walk. Then only so our mountain climbing will be a enjoyable one. Suppose if your box you are putting 100 boxes, so 100 times you are taking a food and stopping and throwing, then it will be weight will be continuously reducing. Similarly, if rocket I am making a 550 or 100 stages, each stage after firing I can simply remove it and I can go. That is a thing. But the problem is when number of stages are increasing, how I will assemble? More number of components will come. So it will lost the simplicity, the reliability will be lost. It will be very problem. Okay, I will make only one stage. The one stage also problem. Say when my stage is already used, why I should take unnecessarily the used stage? So that also problem. So that's why the rockets usually designed to minimum 2 stage to the maximum 5 stage. You can see all the rockets. It will be 2 stage vehicle or 3, 4, 5 till 5 stage vehicle. So once that operation is over, it will be detached from the rocket and it will go. So the detachment time also there will be a separate small rockets will be put, so that will detach the thing. Then how the naming it is given is, suppose assume that there is a main motor. This main motor is not sufficient enough to lift the rocket. Suppose my rocket is 300 ton capacity. So to lift this, I need minimum 1.2 times of the my mass. If I want to lift 300 ton rocket, I supposed to have a thrust of 20% higher thrust. I need a 360 ton of force I am required. So to do that, if I am firing the small motors around the main motor, that is called a strap-on motor, if that strap-on also fired simultaneously with the core, then this is called zeroth stage. Strap-on will be called zeroth stage. Okay. Otherwise, if you take this GSLV rocket, so GSLV all four will be fired along with the main. So we are calling as this is zeroth stage, this is the first stage, this is the second stage, like that we'll call. Suppose like a LVM3 rocket, so strap-on will be fired independently. After this firing is over, second stage will be firing. Like that, we are giving a naming. Okay, how thrust is developed? That is the next question. So there is a fuel oxidizer, it will be burned, then we are getting exhaust gases. So how much exhaust gas is coming, what is the area it is coming, what is the velocity it is coming, this all will dictate. Say mass of the propellant, exhaust gas coming out with what velocity, it will give one thrust. But when it comes out, there will be a delta P difference. So it will come on one pressure. So atmospheric will be one pressure. Say ground only atmosphere is 1 atmosphere. When you go up, so the pressure will be come down. If you cross 100 kilometer, it will be like a vacuum will tell, or it will be below 0.01 percentage. So that also it will generate some thrust. So from there we are getting thrust. Whatever that 360 ton required, whatever I am telling you, that is from this thrust only. Okay, now I will come to answer. What happened from Tipu Sultan rocket to the Hitler rocket? Say 140 years gap. Why it is not happening? Say Tipu Sultan rocket, it was traveling only 1 kilometer. Okay. With that rocket, I cannot make a rocket or a missile which is going to the orbit, or which is firing 500, 600 kilometer of ballistic missile. That is not at all possible. Okay. So that the factor we will call as specific impulse. So the specific impulse will dictate how my fuel is best or worst. That only will give. Even whatever food we are taking, that will be converted into sucrose. The sucrose will be stored in our body. By burning the sucrose only, we are getting the energy. So that is one form of energy. The normal sugar also, it is a fuel. All hydrocarbons are a fuel. If you take this sugar, then it will mix with the potassium nitrate, you fill it, then you fire, it also will act as a rocket. You go to the YouTube and see what is the sugar rocket, you will see this video. So here, what the specific impulse says is, if suppose I am giving a unit weight of a propellant, how much the unit thrust, how much time that unit thrust it is generating. So I am giving, suppose I am giving a 1 kg of propellant. So this 1 kg of propellant supposed to produce 1 kg of thrust. How long it will produce? That is a specific impulse. Suppose it is producing 200 seconds, then it is called 200 is the specific impulse. It is generating something like a 400, then it is called 400. This as much as high, that is the beneficial. The gunpowder which was used in whatever 13th century or by a Tipu Sultan has the specific impulse of 80 or 90 only. So this cannot be used for the modern rockets. Even the sugar case, what I told, sugar and potassium nitrate, that will capable of give something like 120 second. Okay. So simply storing a gas in the balloon will give only 60, 70. But if you take a solid rocket, it will give up to 300. If a liquid rocket, it will be 305. If you go for the cryo engine, it will be 450 seconds. That's why we are going for a cryo. Even semi-cryo will give slightly lower, but however, in handling purpose, it have more advantage. That is the one thing. Then the simplest thing, what is the liquid and solid difference? So it will be more reliable, less system will be there, high thrust can be produced like this, but it cannot be shut down. All these problems are there, but whole world it is shifting from now solid motor to liquid motor due to some advantages. What are the advantages also we will see. Okay, when you fire in a rocket, the inside I told we have to generate the hot gases. So what is the hot gas? What is the temperature? What is the pressure? That was the one interesting question. Say if you take a steel at 1500 degrees centigrade, steel will melt, it will become a liquid. Okay. But this is a Van Braun, he was standing on the Saturn 5 rocket. It has a 5 engine. So you see how big this, it is more than one person height. Say here, the whatever gases produced inside, it will be something like a 3000 degrees centigrade. So at 1500 degrees centigrade, the iron will melt and become a liquid. But at 3000 degrees centigrade, whatever fuel comes, you have to protect the liner. I will tell how it is there. That is the temperature. When even it comes out, the temperature will be something like 1500 degrees centigrade. Second, as high as at what pressure I am by burning more fuel, if I am increasing pressure, my thrust will be increased. Say if you take a Raptor engine, it is firing the propellant at 270 bar. If you take our household cooker, so cooker if it is bursting, it is a big damage. Even that cooker pressure is only 0.7 bar. If you take your car will have only 2 to 2.5 bar pressure in the tire. So it is a 270 bar. It is 100 times of that one. So our rockets are something like a 60 bar pressure it is running. That is a high thing. Second, solid motor if you take, But the beauty of this liquid and solid cannot be fired more. The reason is it is called a nozzle. I will explain the nozzle later part. In general, all solid motor will be firing in 2 minutes only. These are the world biggest solid motor I listed here. But it will generate the huge thrust like this 260-inch motor originally designed for Saturn, but it was not materialized. So 1750 ton of thrust it was generating. Now whatever SLS went 1490, shuttle and all 1200. Our S200 is 515 ton. So if you assume that 3 ton is the one elephant mass, so our even S200 itself can capable of lifting some almost like 150 elephants. That is the one strap on. But two strap-ons are lifting. The total mass of this rocket is 640 ton. So these two strap-ons something like a nearly 1000 will come, but this is average. Starting will be less. It will be lifting. That is the idea. Okay. So we cannot make solid motor in a single piece. There are a multiple piece will be made. It will be joined together. After that, you will have a here one igniter will be put. Okay, here it is there. One igniter will be put. The first this will be fired. After that, if it is a bigger one, there will be a small igniter. After the next level igniter. Then after that, this will have a nozzle. It will go and hit. Then it will fire. Say here solid motor when it is firing, how it has to fire? What is the thrust it has to produce? That we will decide. Why is say suppose my rocket it is standing on the test bed, then it has to start. So when you are going up and up, the density of air is coming down. Okay, if you take oxygen density is higher than the nitrogen. So the lower part, the percentage of oxygen will be higher. When you go up and up, like a peak of Everest, another 20 kilometer, 30 kilometer, the oxygen content will be less. So when my rocket speed is picking up from the earth, something like a 100 kilometer, 200, then 5,000, 10,000 like that. So my speed is increasing, so air resistance will increase. So when I lift the rocket, I need the more thrust. So what we'll call as this curve we'll call it is a M curve. I need a more thrust. So after lifting the rocket, I should not go more faster. So the air resistance will be more. So unnecessarily I am wasting my energy by just opposing the air. So I will go slightly slower speed. Once I am crossing the height of say 15-20 kilometer, we call it dynamic alpha, then my rocket speed will be supposed to increase to gain the more advantage of the delta V. So for that only this M type of curve will be useful for the rocket which is ground lifted. If suppose my rocket is on the airlift, means already I am in the space vacuum, there is no opposition. I will not bother. I will put simply in a circular. So it will be like this. So what I am telling is, say you are seeing here how this casting has done, but it will not be casted the way in which you are seeing. It will be casted either in a circular or in the lobe or in the star configuration or some other configuration. So to get this thrust strain curve, that is the way you have to cast. So when you are mixing all fuel, oxidizer, everything and pouring, then I am firing. This is the thing. Okay, we'll come to the nozzle. So why solid motor is not used more than 2 minutes? The answer is our thermal protection system. So when I am say 3000 degrees centigrade gas is for touching on the surface, so our all metals, majority of the things will melt. So I am putting a mechanism called thermal protection system. We'll call it ablation. So this fellow will be facing this hot temperature. So it will take away the heat and directly it will go to the gaseous stage. Like whatever that Karpuram we will tell now, we when fire it from solid state to the gaseous stage. But every kg of it is going away, how much energy it is taking, that we call the heat of ablation. So it will be face one side like the 2000 degrees centigrade. Other side it will face the metallic component that will be in the room temperature like a 60 to 70 degree. So when I fire the solid motor for the higher number of duration, so this thickness of this layer, the TPS will be going on higher and higher. It will unnecessarily put my mass, so my nozzle design will come down, the mass ratio will change. So that's why no solid motor in the world is designed for more than 2 minutes. But in case of liquid, so I am already using a liquid. So my liquid in the cold condition, either in a room temperature or by in a cryo temperature. So when firing, the hot gases are coming. What I can do is I can pump my liquid, so that liquid can be passed through the walls, like how radiator of a car is works. Then I can maintain the wall temperature, so whatever required temperature. Suppose some metal I am using, it should be 500, I can maintain 500. Once it is coming out, it will be slightly hot fluid fuel, so that fuel can be fed into the combustion chamber, I can fire. So these we'll call as a film cooling concept, or radiative cooling is there, film cooling is there, regenerative cooling is there. There are so many concepts. So due to this, I can fire liquid engine unlimited time. They assume that if you want to put a karpuram, when karpuram is totally fired, then you will not get energy. Suppose you want to fire more number of seconds, then what do? You put a candle, means wick you can put in the vilak. So wick will be the connection point. When you pour the sufficient oil, so oil will travel via this wick, the continuous lightning will happen. So these two comparison you can make. That is the thing. Okay, here it is given. Okay, so now cost of the rocket is very high, I told. Shuttle was the one designed in 1981, it was started. What they thought that they can reuse the shuttle. But you here also you see the total rocket when it was lift off, it is a 2 ton almost, sorry, 2000 ton, 2030 ton. In that the shuttle, the which item which is coming back reusable, only 81 ton. So 81 versus 2000 ton, it is once again the same 1% case only. So there the payload only 27. So that's why the shuttle also was not that successful in the economic point of view. Each shuttle launch was costing something like a 4,500 crore. But instead of that, if I am using a my rocket itself reusable, then the cost will be come down. So that philosophy only now recently people are started using, especially SpaceX and Amazon Blue Origin and all using. Like here concept is like this, it's supposed to be a liquid engine, then the engine will be throttleable. So what I will do is when the stage is over, it is separated, I will bring back the stage by controlling the thrust generated by the engine. So the weight of the mass, if I am generating the thrust, it should be controlled. So I will guide it and accordingly I will get it back to the required place. Then I refurbish this item. The next immediately I will use. So like that they have used more than 15,000 crore money they said by simply reusing the booster of Falcon. So that is the concept now everybody is going. You can see here. So here the beauty is once the solid motor is fired, you cannot control anything. So it will be continuous firing. See our liquid engine also, or the majority of the liquid engine worldwide, see when you fire, so it will operate on full thrust. So assume that your car is there, your car can travel only 50 km/h speed. If you go below 45, it will switch off. Mean how will you control? It is not possible. So that's why when you are putting an accelerator, so your fuel is goes, then the fuel going to the combustion chamber, then slowly we can call here piston cylinder. So your car you can drive either 5 kilometer or 10 kilometer, 50 kilometer like that. So like that version is not available in regular engine. But what they did is in the Falcon, so they made the engine there in the out of this engine, only 3 engine was throttleable engine. So in that throttleable engine, so their thrust can be reduced as low as 30%. So 30% when you are reducing, accordingly the mass of the empty stage you can control. So from there you can bring it back to the required pace. For to understand this, you can just imagine a story. You are taking a water from a well. Okay, you are putting a bucket inside the well. So when the force given in the rope is higher than the bucket weight, so it will come up. If it is lower, it will go down. If you are giving equal forces, the bucket will not go down or go up. It will be under position. So like that, so you calculate the empty mass of the stage. When it is coming down, what is the empty mass? That mass, to match that mass, you fire. Then it will come, it will slowly come. Instead of hitting, I can control this, I can land. That is the idea. Okay. So now, whatever the satellite we told, all are placed something like a 250 kilometer and above. If I want to study the atmosphere, I can put a balloon. So balloon can float in the air till 40 kilometer, where the air concentration more up to 70, 90%. I can study in the balloon experiment. Then what I will do, I want to study the atmosphere, something like a 45 kilometer to 120 kilometer. Regular rocket will not help, regular balloon will not help. For that we are putting a sounding rocket. This is all are called suborbital flight. Once I will fire, it will take to the payloads something like 100 kilometer based on the rocket. Then after that it will leave. It will give a small parachute. So in the parachute, all payloads will be kept. It will be comfortably, it will floating. It will take few hours to reach the atmosphere. During this process, all experiment will be done. Whatever the launching happening in Tumba, all we'll call as a sounding rocket. This will be used to measure this one. Okay, different type of vehicle we told, launch vehicle. If humans are traveling, say if you want to travel from Kanyakumari to Chennai, we will not go by a lorry. So we know that the comfortness on the lorry is not good. We will go to the airbus or a train. Similarly, when human beings are taken to the orbit, the rocket which should have a minimum, one is the saving the crew, second is the load. We will call as a vibration load or G loads. The G load should be affordable for the human being. It should not generate the more thing. So accordingly, it will be designed. This is a normal rocket. If you say this is, then there is a crew escape module also will be there. If anything happened to the crew, so this module, whatever the crew sitting module, will be separated from this and it will be taken away. That is the design. So these all are our regular rocket. PSLV is 320 ton weighs, GSLV 420, Mark 3 is 640 ton. So same Mark 3 rocket will be modified for HLV. So that is a human rated vehicle. So there you can see the top. This is the system. It will take care of human beings. Suppose any problem happened to this rocket at any stage, whether it is the ground or it is going in some altitude, so it will be separated, then it will be safely got. Assume that this rocket is traveling like a 10,000 km/h speed. This crew escape module capable of traveling much faster than this one, and it will safeguard the system. So this is the typical stages are given. So LVM3 have a solid boosters. These all are solid motor. Middle is called a liquid engine. This stage we are calling as a cryogenic engine. So this strap-on will fire separately. So we will call this the first stage. Then the L110 is the second stage. Cryo is the third stage. This three-stage vehicle. Similarly, PSLV having a strap-on, but it will be fired along with the main core. So we will call as a 0th stage. That is the PS0XL, then S139, then PS2, then PS3, PS4. It is a 4-stage vehicle. Then you can see Falcon 9. This is the 9-engine configuration. If you put the same strap on either side, it is called the Falcon Heavy. Then Starship, this is the configuration. So this will generate this much meganewt of thing. This is the bigger one. Saturn 5 was the rocket which was taken to the Apollo mission to the moon. So this is the configuration. The first stage can capable of generate 3,805 ton of thrust. Second stage 575 ton of thrust. Third stage is 115 ton. This is a 3-stage vehicle. That is the thing. Okay. Now almost I told rocket thing. Now the satellite, there are different altitude and different combinations. So many are there. Not only one satellite, the combination of satellite also we are putting. That is a typical example is a global positioning system. This is a constellation of satellite we are putting. Instead of putting one satellite in the geo, I am putting the more number of satellite on the lower Earth orbit. I am controlling doing the same thing. So if you want to control, get the GPS data at any given time, so 3 minimum satellite to communicate. Instead of one, if I am putting a multiple, so all multiple can be communicated. The advantage is when I am placing a satellite near to the Earth, the controlling is simple. If any problem happened, replacing will be simple. These all are small satellite. Instead of putting one 5,000 kg satellite, if I am putting 510 number, even one is not working, I can replace. But one 5,000 not working, it is a huge loss. So like that, there are so many combinations are there. Then even this GPS and all agricultural purpose, avionics, environmental, all this purpose we are using. So beyond this, whatever known satellite application, we need a scientific instrument also. Those things also, those instrument, whatever you call it, also has to be placed in space. The one of the best example is a telescope. If you want to know the how stars are there, we have to see those stars in the by a telescope. But when you put in a telescope, so there are a lot of disturbance, atmospheric disturbance will be there. Like a Kavalur Vainubabu observatory, we can put on some mountain or forest, but till the whatever the stars rays coming from the sky, it has to reach the Earth atmosphere. To avoid that only, we are taken the telescope to the upper atmosphere, that is the above the atmosphere. Some 500 kilometer, we are putting that and we are watching that. A simple example is Hubble telescope. But Hubble telescope also 2-3 times repair was done. it is have some that is visual band only. We were watching the skies and all. But if you want to go out of Earth magnetic things and all, want to see, we have taken the James Webb Telescope. So this was put in 1.5 lakhs kilometer, 15 lakhs kilometer distance. So you see, so this is the Earth. From the Earth at 570 kilometer only, Hubble was placed. So moon was there in the almost 4 lakh kilometer. If you take average, it is 3.84 lakhs kilometer. But Hubble, James Webb was put on 15 lakhs kilometer distance from the Earth. So if you want to go to the long distance, the total mission design itself different. So you have to give sufficient energy to the spacecraft. So you cannot take directly to the launch vehicle there. So this satellite will be have a fuel, so that will be driven. Not only this, if you want to study the universe, there are a number of studies was going on. I want to tell few highlights. In 1974, so 1972 and 73, there is called Pioneer 10 and Pioneer 11 was launched. So you can see here where the Pioneer 11 from the Earth, it was going out of the solar system. But this was life was over in 2003, something like 1,500 crore and 650 crore kilometer it was traveled. Then another two more interesting thing is Voyager 1 and Voyager 2. So in the Voyager and Voyager 2, what we did is we want to see the extraterrestrial life. So one golden coated disc was taken. In the disc, almost 55 minutes, the things were recorded. So I think so many languages in the world and so many sounds, even my animal sounds, everything was recorded. Everything was recorded and it was continuously playing and it is traveling. From 1977 to till now, something like a 2,300 crore kilometer it is traveled. It is almost crossed the solar gravity, and it is from out of solar system it is traveling. This is also one type of mission. For this also we need like other planet like a Venus mission. So we are launching Venus to explore Venus, Mars, Jupiter, all are there. With the Mars mission, I will conclude my thing. So we know that our next neighbor is Mars. If you have a temperature profile and other profile like Earth, Mars also it is a comparable one. There are a number of satellites attempts were made for Mars from 1960 onwards. The list it is given. So recent past there are landers also we are made. Okay, we have landed successfully. Then the one of the Perseverance rover was landed in 2020. Earlier and all the rover will land, it was traveling, but one new attempt was made in this. One helicopter was made called Ingenuity. So Ingenuity, what it does is before the rover was traveling, this helicopter was traveling, and it is going and seeing all the places and coming back and giving a guidance to rover where to travel. So we may think what is the great in putting a helicopter? See, all our flying object, whether it is a bird or it is a aeroplane or it is a helicopter, everything are working principle of producing a drag by generating the delta P. Okay. So that is the Bernoulli's theorem, whatever you are studying. When air is not there, this object cannot fly. So you see the eagle. Eagle, if morning sun rays are not coming, it will not fly, it will wait. When sun rays are coming, the air will be heated, then the heated air is going up, then only using that current it is flowing up. So when the air density was very low, how this flying helicopter is possible? So the such a difficult condition, such a environment, so this was made, then engine was firing. So now next what happened is, the idea is so samples were started collecting from the last 3-4 years. So what is the sample is? We want to know what it is there in the Mars. This is my last slide. With this I am concluding. So there, so the rover was landed based on the other guidance. It was traveling, it was collecting the sample, two sample at a time it is collecting. One it is collected here, so other is on the rover. Okay, rover itself it is there. So every place it is collected, leaving the place some path it is taking. As on today, 27 samples are collected out of 43. So now all the sample, once it is collected, we have to bring it back to Earth, then only we can do our research. But the problem is how we can make a rocket in Mars. Till now we are not have a technology, or our capability of things are not that much. We cannot fly a rocket or lift the rocket from the Mars. So this collection is going on. Suppose the rover, whatever collected package from the rover unable to lifted, the individual thing left over, this is a redundant one, it will be lifted. That is the next thing. If at all any landing and launching the rocket is not possible from Mars, what is the next idea is we will go to the Mars orbiter will orbit. From there we will send one Eagle type of spacecraft. It will go there, it will not land, it will pick up this whatever collected sample, it will come and come down. So it is a huge cost involved item, but still the rocket technology is going on evolving to meet this such a requirement. So that also it is going on. Okay, with this I concluded. So whatever I have told in my presentation can be seen detailed way in few of my books. The one book on unlocking the mysteries of rocket science. The second book on the Sky Rider. So this book will give about all this detail. Then the third book is the second trip to the moon. Then the fourth book is the biography of one NASA scientist. So he is the planetary protection group head earlier. He is retired now. So he is taking care of this microbial loading. Whatever Mars I had told, how much microbe is going to the other planet, how we are bringing back, what type of test we are doing, like International Space Station. So what sample we are collecting and bringing back, and what test we are doing, why we have to study microbe. All those things we can find. Similarly, this microbial marvels also will explain how this microbe affect day-to-day life, even space also. So with this, I am concluding my thing. Any doubts is there can be asked. So if you want further details about this book, you can visit this website writersasi.com, or this mail ID is there. Okay, thank you, Anandal.
Okay, sir. We are in final stage of sixth session. Word of thanks. I would like to take a moment to express our heartful gratitude to our esteemed resource person, Dr. P. Sasikumar, for taking the time to share their valuable insights and experts with us totally, who has gave a lot of information regarding role of rockets in space exploration. We are very thankful to you, sir, and also thankful to all supportive staff members of Macet family, and thankful to other participants from various colleges. Once again, thank you, Dr. P. Sasikumar, for your outstanding contribution to our event. We are deeply grateful for your support and look forward to future collaboration. Thank you, everyone presented here. Thank you, sir.
Thank you, sir.
एगो कहत रही हम करे के नहीं उठबे तब हम काम नहीं पर करे के देखियो ये पैसा हम कहले पैसा अपना जगह पर छे पैसा ले तो हम कहते छिया त हमरा समय हमर देखली दुनू टा केहन रहे चा हम बजे ओकरा ले हम देवी तो देहा केहन समय रहे